Hi everyone. It works, perfect. Thanks for the introduction. Thanks for having us and giving us the opportunity to talk an incredible 4 hours on causality. So we can talk about what we like the most, causality. Please make this fun. Ask questions, interrupt, ask about what is unclear and get a conversation going, because we won't be able to cover all of this, but we should be covering what you are interested in the most. So I'll just jump right in. The motivation. Why are you here? Why are we here? What is there to talk about even if we have a tutorial on causality? So as most of you are probably reading neuroimaging or neuroscience papers from time to time, I hope at least, you may come across nice discussion sections like these, where you can read hippocampal activity in this study was correlated with amygdala activity, supporting the view that amygdala enhances explicit memory by modulating activity in the hippocampus. So as a causality person, this is a lot of bell ringing going on here. There is a word correlated, there is a word enhances and modulating. So correlation is a statistical term, and enhances and modulating are causal terms. So I would just intuitively, for now, write down this graph and tell you what is written here in a graph language would look like this. The amygdala enhances explicit memory via modulating the hippocampal activity. So now the question is, how can we actually go from this statistical term, correlation, to these causal terms, enhances and modulating? So what I'm saying here is, I think the motivation is, if you want to write paragraphs like this, you are interested in causality, so we should understand when can we talk about causality and infer causality from observed data.
Hello. So since, no, I can do it. Okay, so first one should say, you will see that from the second example even more, that drawing causal conclusions from statistical data is hard and will remain hard. So don't expect an algorithm where you just plug in your data and it just shows the causal structure. So applying existing algorithms in a sensible way requires deep understanding of the problems of causal inference. So this course will provide a basis only for that. And as an additional motivation, since I don't know much about brain research, example from everyday life, recently I read about a study that reports that children who grew up in a household without dishwasher tend to have less allergies. And a possible explanation is that the stronger exposure to bacteria helps development of the immune system, which is quite consistent with several other evidence on the statement that exposure to microbes in early childhood is good for the immune system. But of course, we can't conclude from that study that really the missing dishwasher is causally responsible for helping to prevent allergies. So the relation between statistics and causality is tricky. And what I also like about this example is that typically the most relevant problems are the hardest ones. So don't expect that we can solve it today, this problem. But we can talk about how one could address that in principle. So just to recall that and emphasize that statistical and causal statements often differ by slight rewording, and that's sometimes a problem with our usual language, that children growing up without dishwasher are less likely to have allergies, sounds close to children growing up without dishwasher are less likely to have allergies because of the missing dishwasher. So the first one is a statistical statement which can be tested by standard statistical tools. And the second one is the causal statement. And no standard methods available, and the tutorial will only give partial answers. So, given these problems, the question arises, does statistics tell us something about causality at all? And at least there are interesting axioms and very helpful axioms, and I think among the earliest ones is Reichenbach's principle of common cause, stating that whenever two variables, do you see the red dot a bit? Okay. Leave it for now. Whenever two variables x and y are statistically dependent, then either x causes y or y causes x, or there's a common cause set of both. So every statistical dependence is due to a causal relation. We also call two causal. Sometimes terminology in the literature is not consistent in this regard. Some people call this acausal as well. And distinction between these three cases is a key problem in scientific reasoning, but even worse, the cases can occur simultaneously, of course. So, in order to address those hard problems, we need to formalize causality. And one of the people who contributed most to formalizing causality is definitely Pearl in his book Causality. And Pearl defined the functional model of causality, sometimes also called nonlinear structural equations, which read as follows. I would like to use this paper, this pointer nevertheless, if more than half of the people see it. It helps myself focusing. So let's say the model says that every node xj, so here's a node xj, is a function of its parents and an unobserved noise term. So here are the parents. And then one assumes that all the noise terms are statistically independent. So this is basically a matter of definition. So whatever is not independent would be explicitly modeled as a variable, but on unobserved noise variables that are independent can be modeled as noise. We can also talk about that, about the motivation for this approach later on. Okay, and the idea is that these functions do not only describe statistical relations between the variables, but also causal relations in the sense that setting those parents to some specific values changes xj in a specific way. So that's important. So there's really causal semantics behind the functions. And although in practice you never know those unobserved variables, or I would say typically you don't know them, it helps you thinking about causality. If you think of an unobserved noise term, that makes the probabilistic element in this structure. But then Pearl asked which properties of the joint distribution follows from this model of causality. And there are 4 equivalent versions. Basically, there are even more, but I think that's the most important ones. So the existence of such a functional model with the independent noise term is equivalent to the local Markov condition, stating that every node is conditionally independent of its non-descendants given its parents. So here is the node. Here's the parents. Here are some non-descendants. So given the parents, this is independent of that one. So every information exchange with non-descendants involves the parents. Then there's also a global Markov condition, and this is one that I will explain more explicitly later in further slides. It describes all independencies via deseparation. The idea is that the Markov condition, this local Markov condition, entails further conditional independencies implicitly, and the global Markov condition states explicitly which ones are entailed. Then there's also an equivalent condition that is very intuitive, the factorization. It just states that the joint distribution factorizes according to the graph. So the joint distribution is a product of the conditional distribution of every node given its parents. And for causality, it's quite crucial that we consider those conditionals as representing the causal mechanisms. So they are not just mathematical objects. You can factorize the joint distribution in many different ways, but this is the one that describes the causal mechanisms. This is related to some slides that we have later on, that this conditional independence holds in a quite different, broad sense, so not necessarily with respect to statistics. So if you think that of genes, for instance, of a person X, if someone knows the genes of X parents, neither the genes of the grandmother nor the genes of the brother contain additional information about X. So given the parents, these persons are conditionally independent of person X. So this is a non-statistical version of the causal Markov condition in a way. Okay, but what is important also in practice is the global Markov condition. I said that the local Markov condition entails further conditional independencies in the following sense. If you have this chain, then maybe it's quite intuitive for you already that X is independent of W given Y, because Y is on the path between those two variables. But this independence does not directly follow from the local Markov condition, although it's true, but it follows by combining independencies of the Markov condition and applying rules that generate conditional independencies from known ones. Okay, but I said the explicit formulation about which independencies are implied by the local Markov condition is given by the graphical criterion of deseparation, and this is what I will explain later, but maybe just as a reminder that we often need to distinguish between statistical independence versus uncorrelatedness. So independent means that the probabilities factorize, while uncorrelated means that the expectations factorize. In the physics literature, it's not really consistent, but in the math and statistics literature, it's consistent. And independent implies uncorrelated, but not vice versa. And you can reformulate statistical independence also about, in a way that you say that all functions of X and Y are uncorrelated. So this way you get a condition that is equivalent. Here's an example of a joint distribution of X and Y, where X and Y are dependent but uncorrelated. And you can show that they are uncorrelated from symmetry arguments. I don't want to go to that. Okay, but deseparation is a quite important concept. And I mean, the details are less important than just the fact that it's a graphical criterion. So roughly speaking, you define a notion of blocking of paths. So a path Q, so a path consists, is a chain of edges, is said to be blocked by a set set if Q contains a chain IMJ or a fork IMJ such that the middle node is in Z, or Q contains a collider, this is called a collider, IMJ, such that the middle node is not in Z and such that no descendant of M is in Z. Z is said to deseparate X and Y in the DAG G, formally denoted this way, if Z blocks every path from a node in X to a node in Y. And just some examples. So X and Y, and the path between X and Y is blocked by conditioning on U or Z or both. The path from X to Y is blocked by the empty set. This is important because here you have a collider. So the fact that X and Y have a common effect does not create any dependence between them a priori, but it's unblocked by conditioning on the common effect or an effect of this effect. And this is a paradox I'm describing later. Here, maybe I don't have to go through all the examples here. So the unblocking by conditioning on common effects is a popular paradox, selection bias. Let's say you have 3 binary variables, X, Y, and Z, and Z is just X or Y. For instance, you assume that the language skills and science skills are independent a priori for children, and then you assume that pupils go to high school if they have good skills in science or in languages. Then in high school you will find a negative correlation between science skills and language skills. It's just a toy model, no matter whether it's really true in this sense. Okay, and this unblocking of paths by conditioning on common effects is an interesting asymmetry between cause and effect. So if X and Y influence Z, then they are a priori independent, but get dependent by conditioning on Z. While if Z is a common cause of X and Y, they are a priori dependent, but get independent by conditioning on Z, on the common cause. And this asymmetry has been described by Reichenbach in the book, The Direction of Time. It's actually a physics book. It's a book about thermodynamics, the difference between past and future in theoretical physics, where he considered this asymmetry as part of this asymmetry of past and future in physics. This famous question, why do photographic images show the past and not the future, which is for theoretical physicists an important problem and not obvious at all. Okay, but if we consider the correlation between having a dishwasher and getting allergic, then it's important to see the difference between seeing and doing. So we have observational probabilities. P of y given x is the probability for the variable y to attain the value y, given that we observed that x attained the value x. And there are interventional probabilities, P of y do x. It's the probability for y attaining the variable the value lowercase y, given that we have set x to x. And I would say that confusing P of y given x with P of y do x is the reason for most of the common misconceptions about causality. And also in theoretical physics, I have seen many discussions where all the confusion was due to this difference. Okay, and to formalize this difference, Pearl has created a very nice framework. So he defined this do operator in the following way. It's actually a simple thing if you understand it, and it's in retrospect quite straightforward. How to compute the joint distribution of x1 to xn given that you set one of the variables to one specific value. Let's say the variable xi is set to xi prime. So you first write the joint distribution in the causal factorization according to the third Markov condition that I mentioned. So each xj given its parents. And then you replace the conditional of variable xi with the Kronecker delta. So xi prime, which attains the value 1 if the two values coincide and 0 otherwise. And okay, so you do this replacement just because this is the variable you intervene on. By intervening on the variable, you cut the relation to the parents. And this way, you get this expression. You can interrupt me at that point. I appreciate questions. Yeah.
Maybe this is where you're heading. All of the conditional independencies that you just covered, do they still apply whether you do X or merely conditional?
Oh, that's an interesting question. Yeah. Ah, okay. So he was asking whether the conditional independencies that we had before for the observational probabilities still apply for the interventional probabilities. They do, but there are even additional ones because you cut dependencies to the parents. Okay, so and then you marginalize, let's say you are interested in the effect of xi on the variable xj, then you marginalize over all the remaining variables. So this is the expression, and that's it already. And to see a few examples, you can check that easily, that for one, interventional and observational probabilities coincide. So if x is really the cause of y, then p of y do x is the same as p of y given x. If the entire relation between x and y is just due to a common cause, then intervening on x does not change y at all. So p of y do x is the same as p of y and therefore not the same as p of y given x. And the same for 3. If y is the cause, intervening on x does not change y. Okay, but these were the simple cases. The most important non-trivial case is the following. You have x influencing y, but on top of that, you have also a common cause influencing both. So of course, it's hard to tell what part of the dependencies between x and y are due to the common cause and what part is due to the influence of x and y. And this do operation separates the two in the nice way. So what you need to compute is just this expression. So it differs from p of y given x just by replacing p of z given x by the marginal distribution of p of z. So the reason is because due to the intervention on x, so let's say you randomize x, then it no longer depends on, then z gets independent of x, and therefore you need to replace that. And I would say that maybe 80% of causal inference I have seen in industry is about this in a nutshell. So applications, this set is multidimensional, can be 500,000 dimensions or something like that. So you get a lot of statistical issues and can't really apply this formula. And therefore, you need other approaches. But the idea is still that one. Okay, it's up to you now.
Before I continue, I also have an important announcement to make. We have a third mic. So if you want to ask questions, and you should ask questions, use the mic. As an additional motivation, I've just moved to Copenhagen and cycle a lot now, which I haven't done before. But now I came here to Berlin and haven't cycled today, so I can run around the entire room to bring your mic. Just make me run around. Or you want to run around, but then I really missed my cycle this morning, so we can take in turns maybe. Any questions about what we've seen so far? Yep. Here's the run.
I'm not sure it's actually like a proper question. It's probably just if you could just like go back a couple of slides so that I can just check something I was writing down, and then a couple forwards. Yeah, that one. That one. No, the next one. Brilliant. Can I just copy a couple of things from that slide?
Yes. Also online, so.
Brilliant. So that answers the question.
All right, perfect. Okay, so now we've seen another question.
So all these definitions, are they equivalent, or is there any case that they don't be equivalent?
So the question is, are the definitions all equivalent? You mean the definitions of causality? So far we've only introduced basically functional models. So the Pearl idea that every node is a function of its parents plus some independent noise term. And then we've talked about how this manifests in conditional independencies in the data, and how you can use this do operator framework to evaluate certain quantities you might be interested in. So let me jump back to this slide. If you know that this is the causal model and you want to evaluate P of y given do x, then this is how you do it. That's why it's nice to have this framework. Now the question is this similar or equivalent to all the other notions? I think everything we're presenting today, I'm not sure I should use the term equivalent, but it's all the same idea, the same concept of what it means to be a causal relationship between two variables. Maybe as we go along, keep the question in mind and ask again if you think like, what is this got to do with the other definition or concept of causality? Does that satisfy your, yeah?
So I'm still, just sort of trying to understand the difference between conditioning on x and conditioning on do x. So does this framework allow you to define a posterior over do x as opposed to x? So basically, it will give you, the posterior on x given, its relationship to y given x. But can you infer that x has been done? You see what I mean?
I think it was two questions. I'm not sure. So the first one is, can you infer a posterior over y if you have done x? And the second one, can you see whether you have done x? I think it's two separate questions. So the first one, if you have the causal model and you're interested in the distribution of y given you have done x, that you can now evaluate. Under certain conditions you can. So let's say, maybe let's give some meaning to these variables. Maybe that is smoking habit, that is lung cancer, that's the classic. And then this might be your genetic disposition to become a smoker or to develop cancer. If this is how you model and you truly reflect the relationships between those variables, you can now ask the question, what happens if we make people smoke? You can now evaluate this. And you can account for maybe different genetical dispositions increase both the likelihood of becoming a heavy smoker and also to develop lung cancer because you're kind of an unhealthy type in general. So the cool thing now is you can evaluate this quantity. Given you have the model and you write the functional model down, you can now evaluate the posterior over Y. Does that address the first question?
I was more concerned about posterior over do X. If that's even a definable object. I mean,
In what sense?
well, can you take a set of observations and infer that X has been, I don't know, acted upon or done? I don't know. Maybe it may not be the most.
I think
It seems
P of 2x given y makes sense.
Right. Yeah.
P of I can imagine of a framework in which you can address this question. Should I briefly explain? Yeah. 1 minute. Okay. So let's say one approach to define the difference between seeing and doing is that you introduce auxiliary variables that define this intervention. Let's say this is some variable. If it attains the value 1, you intervene on X and set it to one specific value. And if it attains 0, you just keep the value it has been before. And then your question would just be a conditional distribution, for instance, P of fx given xy, right?
Yeah. Yes.
Okay. But you always have to keep in mind that you induce a different distribution, so it's not the usual Bayesian update.
My question is there are many, say you have a distribution of many variables, there are different ways of factorizing it. If I do 2x in one factorization, is the distribution I get the same as if I did 2x in another factorization?
No, it's not.
Okay.
So all the factorizations give you the same joint distribution, but only one is the one that is compatible with a functional causal model. So I think maybe we actually have that on, let me see. Okay, let's say 1 and 3. If you have a bivariate Gaussian model, you can either model it that way or that way, which means you can factorize the joint distribution over x and y both ways equally well. If you now do x, and the true underlying model is the first one, but you factorize it like this, your factorization on this side would say there's no change in y. Whereas if you had gone for the true causal factorization, then you would infer indeed a different distribution now on y, given that you have set x to a specific value. So it's quite relevant at this point. The joint distribution is the statistical thing, and we're trying to infer something about the factorization that is more than just any of the factorizations. I think there will also be another slide on this later. But
yeah, but maybe we could also add that the problem where the graph comes from hasn't been addressed so far at all, so this will be addressed later anyway.
So that's basically doing something depends on the graph.
On the graph, definitely, definitely, yeah.
Even though this is
Yeah. So even though they are Markov equivalent, have the same independences, it does make a difference.
maybe a slogan that helps to keep in mind, at least it helps me, causality is strictly more than all the properties of the one joint distribution that you've observed. Once you intervene, you have to decide something which is not entailed by just looking at the joint distribution in the observational setting. Maybe that helps, maybe it doesn't.
Since you brought out this slide now, probably just a very silly question, but the difference between case 2 and case 3. So I can see that the probability of y is different from the probability of y given x in 2, I think. But if you do x on the third case, why is the probability of y different from y given x? So if I'm changing x and x is not affecting y, why is the conditional of y given x different from just y? I don't know if it makes sense.
The question does make sense. Okay, maybe it helps again to give names to these variables. So this is feeling tired, and this is having slept a lot, and this is feeling tired. If I now observe a lot of people feeling tired, which is conditioning on x being tired, I know more about y. I know that it's more likely that you haven't slept a lot last night. So that changes the distribution of y. Whereas if so now with this example it doesn't really work out, but if I see you in the room and I make you look tired, so maybe you put up some makeup, that doesn't tell me anything about your last night's sleep, which is the difference between doing and seeing. Does that give you some intuition and answer the question? Yeah? All right. Oh, that's great. Sorry? The slides are online, yes.
QR code.
So I can either go back to the QR code or you Google my name if you remember it, but maybe let's just do this thing. Here we go. So it's either the QR code or you Google my name and then search for slides. You will also find it. Okay, I'm going to wait for people to take QR code photos.
Feel free to get together.
Otherwise, maybe it's s.weichwald.de. So you can just. Okay. Oh, still. Sorry. Okay. Functional causal models, do operator, statistic properties entailed by the functional model. Now we are talking about potential outcomes framework. So far we've talked about distributions. Now we will talk about something like looking at individual, let's say, persons and individual samples that we've observed, and then asking questions about what would have happened had I given this person an aspirin instead of an ibuprofen. So we're now talking about individuals instead of the statistical sample properties. And this is nice to think about in the potential outcome framework, but it's linked to what we've heard before, because for each individual that you've observed, so you draw a sample from this distribution, that means now every noise variable has taken on a particular value for this one person, let's say. And then you have evaluated all those functions in the right order implied by the functional causal model. Now you can ask this question, what would have happened had this noise variable been 5 instead of 4? But now we're zooming in on one particular case, basically. So the math now looks a bit different, but it's related, so it's basically the same concept. We start, what are the ingredients? We have a population U of units, so we call units U in this set U. So let's say, that doesn't work anymore. We have a patient group, and then we add in a treatment variable. So some of those patients get a treatment and some others don't. So we map each unit in U to either receiving the treatment or being in the control group, not receiving a treatment. So yeah, That's what I said. And then we have the potential outcomes. And now we need to pay attention to what is written here. So we map each individual and value of TOC, so whether the subject was in the treatment or control group, to the real valued outcome. So we can, for each individual unit, we can evaluate, let's say, unit U, comma T, and the value of U, comma C in this framework, which will be important on the next slide. So let's say we can look at survival times of the unit U when we gave the treatment and unit U that wasn't exposed to the treatment. So why is that problematic, or where is a problem, or what do we even need to talk about now is the fundamental problem of causal inference. So what I've just defined is a nice mathematical object, but there's a problem in practice. For each individual, we can only observe one of those two values. Without further assumptions, there's no way I can observe both values for one unit. So in that terminology, the treated unit outcome and the control unit outcome cannot be observed at the same time, so I cannot possibly evaluate this value. I cannot tell without further assumptions what would have happened had you not taken the aspirin if I only see you taking the aspirin. So what can we do? We can add in further possible remedy assumptions. So in general, that's a general scheme. There is no causality without making assumptions. You need to make assumptions, they need to be discussed and need to be plausible. Without assumptions, you're just stuck on slide 1, basically. So one assumption could be, maybe the units are homogeneous in the way that a treatment unit, U1, looks exactly the same to a treatment unit, U2. And a treatment control unit the same. So if I observe this guy here, unit 1 being in the treatment group, I can just compare it to treatment control group unit 2. And the two values would be the same, so I can just compare the two values. It's one additional assumption. Another assumption would be, maybe I can give you an aspirin today, and next time you have a headache, I don't give you an aspirin. And maybe those two values are actually the same thing, with a strong assumption, because taking an aspirin on Mondays could be different to taking aspirin on Wednesdays. So this is additional assumptions that make this thing work. We can also do another trick, kind of, or talk about a different quantity, which is the average treatment effect. So instead of zooming in for one individual, we can talk about, on average, taking the aspirin helps or it doesn't help. So now we're talking about averages over those quantities. Still, that doesn't solve the problem, because we can only observe this guy, which means the average outcome for treated, given that they were actually treated, and the potential outcome of the control group, we can only evaluate for the actual control group. So we're still stuck with this problem. So there's another help. If we randomly assign treatments, and we all know this, if you randomize treatment, the world is nice again somehow. So that is expressed by this maybe cryptical looking condition. So the assignment, so the decision, do we observe this potential outcome or this potential outcome for each individual unit, is independent of what the values of these potential outcomes actually are. If this is satisfied, then you are better off and you can actually estimate these quantities. Because then this guy here is equal to this, and this guy here is equal to this, and now you can evaluate the average treatment effect. Let's do an example. The classic example is coffee, cancer, or smoking and cancer, or like any one of those examples. So now we're asking, does coffee consumption cause cancer? We split the population U, and we're doing kind of a twist. We're not talking about treatment, we just split the population according to, it's a heavy consumer or it's a little consumer. So we have the units U that have consumed little coffee, indicated by this empty square, and then the units that have that have consumed a lot of coffee, they have a lot of black intake, they're indicated by a black square. Now we observe whether they suffer from cancer or not. So that's the potential outcome. For each person, if I draw, there could be an outcome for this person being a heavy drinker, having consumed a lot, or having not consumed a lot of coffee. But we only observe one of those two outcomes. Now let's assume that older units have a higher cumulative coffee consumption. It's a quite plausible assumption for this scenario, as well as an increased risk of cancer. So now I'm adding something in that basically violates the randomized treatment assumption. So now I'm giving an example of what goes wrong. If this is the case, so it looks like this. So I'm also putting in this slide because I feel thinking about causality in terms of graphs and functional models can be much more intuitive and helpful, but it's a choice. But I'm adding this in here because what I've just talked about in a graph language is quite easy to convey and summarize. The age influences how much coffee you have taken and how much chances of developing cancer you've had. So the graph looks like this. We have now strongly violated the assignment or the splitting of units into treatment and control group, because the older a unit is, the more likely is we put it in the pool of heavy coffee consumer. The younger a subject is, the more likely it is to put it in the lower consumption coffee group. But also for younger subjects, these two values are probably lower, and for older subjects, both values are actually higher. So this independence is violated. If we do this, for example, and try to estimate the average outcome for low coffee drinkers, we can only evaluate this quantity, but this quantity now is strictly smaller than this, because if we only look at the younger subjects, they will have a lower value of y square, empty square, for two reasons: having less coffee consumption, but also being younger. So if we now estimate this average treatment effect by doing this estimation, we systematically overestimate the effect of cumulative coffee consumption on cancer. I think it's good news. Maybe coffee drinking is not that bad after all. So now we've talked about the potential outcomes framework, zooming in on individual units. You need additional assumptions, otherwise there is no hope. If you now go to statistical quantities, you need also additional assumptions. And now we've seen a violation of this assumption and what goes wrong if you violate actually this assumption. So I've built up to this point. Strong assumptions that enable causal discovery is the next topic that we talk about. Are there any questions at this point? No.
No, I can take that one. No. So maybe one could add that these two frameworks, like these potential outcome and the graphical model frameworks, have been sort of competing frameworks. I've seen quite emotional debates about that. Meanwhile, it's calming down. So maybe since 10 years, it's calming more and more down, and people switch between both types of languages and see it less emotional. Who
won this debate?
Oh, well, it's hard to make a statement in public about that. I prefer graphical models, definitely, but you can translate it. Okay, so far we haven't been talking about how you get the graphical model in the first place. And one has to admit that it's still a very hard problem, and maybe there's also something that has been oversold in the past. But it depends heavily on strong assumptions, and there are good reasons often to make strong assumptions, and then you can also infer the causal structure. So if you are given a joint distribution, or more realistically speaking, you are given instances from the distribution, then the Markov condition describes which sets of DAGs are consistent with the distribution. But there are n factorial many DAGs that are consistent with any distribution. So these are the complete DAGs, where you just define an arbitrary order and draw an arrow from each node to each node that is further down in the order. And this is consistent with any distribution. So we need reasonable rules for simple DAGs, how we get more plausible DAGs. And one philosophical principle, it's not obvious how to implement that at all, but I will show you how it will be implemented in practice, how something can be done that is in this spirit. So one important philosophical principle is the so-called independence of mechanism. It says basically that the conditionals P of xj given its parents in the causal factorization represent independent mechanisms in nature, and therefore they don't contain any information about each other. And one formalization that we proposed was via algorithmic information theory. I will talk about that later a bit, which means that the shortest description of the joint distribution is given by separate descriptions of these conditionals. And the reason why this is believed to be the case is that is the philosophy that those independent mechanisms change independently in nature. I will show you an example about that. In our book you will find a quite extensive discussion of the history of this principle. So there are many facets of this principle. I can't mention all of them. So just for the bivariate case, because it really contains very non-trivial statements already for the bivariate case. So, which means that, for instance, P of cause and P of effect given the cause may change across environments, but they change usually independently, which means knowing how P of cause has changed does not provide information about if and how P of effect given cause has changed. And knowing how P of effect given cause has changed does not provide information about if and how P of cause has changed. To show you a practical example, so this is a drawing of a ball track, and this is from data that I really recorded at the ball track of my daughter. Here is the position of the ball, and here is speed measurement. It's basically two light barriers that measure just the time for passing the ball needs for passing. And the x, the cause is the position of the ball, and the speed is the effect. And of course, the distribution of this position would change if another child plays. For instance, if it's an older child, it will maybe put the ball here. And P of effect given cause changes if the light barriers are mounted at a different position. So if you just move that to a different position here, then you change P of effect given cause. But it's hard to think of operations that change P of effect without affecting P of cause given effect, or vice versa. Which is not supposed to mean that this wouldn't be possible. It's just the statement that this required hand tuning. So if you change this position and mount the speed measurement as a different place in some way that is adjusted to each other, then you can ensure that this happened. But typically, they change independently. And another implication is of this independence principle is for causal and anti-causal learning. Causal learning would mean that you try to predict the effect from the cause. For instance, predict properties of a molecule from its structure. And anti-causal would mean you predict the cause from the effect. for instance, tumor classification or image segmentation. So there are a lot of anti-causal learning problems. And a hypothesis that we published together with Bernhard Schölkopf and several former colleagues, that semi-supervised learning, for that reason, only works for anti-causal learning and not for causal learning, because P of X wouldn't tell you anything about P of Y given X. And that has been confirmed by screening performance studies in the literature. So we haven't found any successful case of semi-supervised learning for the anti-causal, for the causal learning scenario, just for the confounded scenario or anti-causal. Just to give an intuition about that, so let's say, for instance, Y could be some class label, for instance, male or female, and let X be a feature that is influenced by X, for instance, hate. Then let's say you have a very simple model where P of X would just be bimodal, and this would be females and this males or whatever. And then if you observe those two modes, then it's quite likely that each mode corresponds to one class. And this can easily be confirmed by observing a small number of labeled points. However, if you're in the causal prediction scenario, so let's say Y is some class label of an effect, and X be some feature. For instance, Y could be whether somebody is sick or healthy, and X would be some feature that influences the disease, some risk factor. Then if you observe that X is bimodal, then there's no reason to believe that the modes correspond to the two different class labels, because the modes are generated by upstream causes and not by the class label, which is downstream. Okay, so this is one of the facets of this independence principle that we short call ICM. But for causal discovery, an important one is so-called causal faithfulness. And it means we prefer those DAGs for which all observed conditional independences are implied by the Markov condition. And the idea is that generic choices of parameters yield faithful distributions. For instance, assume for this simple DAG you observe that X and Y are independent. Then this would be a violation of faithfulness, because then the direct influence of X on Y would compensate the indirect one, which means that the parameters of these models need to be adjusted to each other. And how does this relate to ICM principle? I mean, the reason why we reject that is basically that our model of nature assumes that nature is, so to speak, randomizing parameters at each node or at each edge in this case, if it's a linear. Let's say, for instance, you have a linear model and you sample those coefficients randomly, then you observe that with probability 0. So therefore it's unlikely and we reject that. There's another example of unfaithful distribution with a linear model. Okay, and conditional independence-based causal inference uses causal Markov condition and causal faithfulness, and it accepts only those DAGs as causal hypotheses for which all independences are true that are required by the Markov condition, and only those independences are true. And then you can identify the causal DAG up to Markov equivalence classes, which is the DAGs that imply the same conditional independences. Okay, that's yours again. Any questions to that? Yeah?
Just on your example, again, it's an example you gave under the molecular structure gives the properties, right? You would expect that you could just use supervised learning for that. Why is it?
You mean, sorry, this example?
No, the example on the previous slide.
Yeah, this one?
Even further back. So here you have the causal learning, building properties from a molecule from its structure. And then you say you can't learn that very well with supervised learning.
In semi-supervised learning. Semi-supervised learning. So so the unlabeled examples wouldn't help you.
Okay.
Yeah.
Okay.
The labeled ones, of course, help. Okay. Yeah. That's yours. More questions?
Okay, so we're talking about conditional independence-based causal inference. This is an example in neuroimaging. It's not an actual study, but it's a potential application of this idea. So let me go back one slide. Conditional independence-based causal inference makes two assumptions mostly, the Markov condition and the faithfulness condition. So all conditional independencies that you observe are implied by the causal graph, and these are the only ones that are implied by the causal graph. Now there's algorithms that exploit these two conditions to infer the causal graph or an equivalence class of graphs from observed data. So maybe buzzwords, putting buzzwords out there. There's the FCI algorithm, fast causal inference algorithm, or the PC, Peter Glummer algorithm. But now we're looking at one particular case, because sometimes it's easier to actually look at one zoomed in problem instead of trying to solve the full-fledged problem where you observe and test all the conditional independencies and then you've come up with this master graph of everything. So now we're putting up a scenario that is maybe not that implausible to encounter when you actually run a neuroimaging study, and then we see how these ideas manifest and how you can do causal inference in this scenario. So let's start with a study with a randomized stimulus S. Let's say we present, I don't know, cat and dog images maybe to subjects in a scanner. Maybe that's a good idea. And then we observe neural activity X and Y. Let's say MEG activity in two different lobes, or fMRI voxel activity in different voxels X and Y. Let's make it really simple and only talk about these three quantities for now. If you do this, let's say we put aside all the statistical problems for now. It's a big assumption, but just to make clear how this works. Now we estimate the joint distribution of the stimulus, the X variable and the Y variable. I've put up this null symbol up here, which means we haven't otherwise intervened on the system. So we just put people in the scanner and recorded the activity when presenting randomized stimuli to those subjects. Let's say in this joint distribution that we have observed, so we have observed one distribution, the observational distribution. Assume that we find the stimulus actually is dependent on the X variable, which is easy. Correlation analysis, for example, could confirm this. You find if you present cat, then this lights up. If you present dog, then this doesn't light up. Let's say, okay, let's first do this. So if you find this, we can conclude that the existence of a path between S and X without a collider. So in the causal model, there now needs to be a path from S to X. Otherwise, you cannot explain why they should be dependent. Somehow S needs to be caused by S. Otherwise, you wouldn't find a correlation. This is only true if you make those two assumptions, Markov and faithfulness. Let's say you find similarly that also the Y variable is dependent on S. So if you present cat, it doesn't light up. If you present dog, it does light up. There also now needs to be a path from S to Y without a collider. So these two statements by the causal Markov and causal faithfulness assumptions implied and gave us information about the causal graph already. We know there needs to be two paths, one from S to X without a collider and one from S to Y without a collider. And they need not necessarily be different paths, but these two paths need to exist. Let's now further add in a conditional independence. And usually if you run conditional independence-based causal inference, the independencies are the interesting things to look at. So let's say you present a stimulus, you find those two brain areas to be correlated with this stimulus, but for some reason you find if you account for X, then the stimulus doesn't tell you any more about Y. So let's maybe talk regressions. If you regress out X from Y and the stimulus, suddenly it becomes independent. It's kind of funky that you can find this, because both are dependent, heavily dependent on S. But let's say you found this to be true. Then all paths between S and Y need to be blocked by X. Otherwise, there's no way of generating this data. If we now put these three things together, and you can try on a piece of paper if you can find a counterexample. I'm pretty sure you can't, but if you do, let us know, because then we have a big problem. If you find these three properties, you can rule out cases where S causes the activity in X, but where there's some hidden stuff going on in the brain that causes both X and Y. You can rule out this. It's not compatible with these three observations. And it's pretty cool, because if you can rule out this, you can actually formally prove and conclude then X is a cause of Y. That means you basically have S arrow pointing to X arrow pointing to Y. That is the only graph to explain this under the causal Markov and faithfulness assumption. So now by running this study, you have established a causal link between two what we called brain features, X and Y. But you've only randomized the stimulus outside of the system, which I think is pretty cool. So now you can talk about causal relationships between brain activity, brain features, by combining these different things. So we have basically put in three ingredients: causal Markov condition, causal faithfulness condition, and the assumption that we have randomized S. This is crucial, otherwise it doesn't actually work this way. But in a neuroimaging study, that might actually be a plausible scenario you end up in. So, no problems with hidden confounding in this case. There's an actual application now. A study by Bach and Dolan about probabilistic reward prediction. So they have MEG scans of people who need to predict a reward. So the idea is you present these 9 different stimuli. Each of these stimuli is associated with a different mean reward and variance of reward. So the mean is encoded in the filling of the circle. If it's fully filled, you can see the mean is always 1. If it's half filled, the mean is always 2. If it's empty, it's always 3. And the color is associated with different spreads or variability of rewards. So blue here has least variance and red here has highest variance. You present these different stimuli in a randomized fashion. You also randomize the mapping between rewards and variance to the colors and fillings of the circles. And you ask people to press 2 buttons. One is indicating the color and indicating the filling. And if they correctly do it, they get a reward according to what stimulus was presented. People get trained in the MEG scanner how this game works, and then you observe people being presented with this randomized stimulus, and they press the button. So that's randomized S, and we observe X and Y. At that point, and they actually also did do this analysis, they've screened for all features that are correlated with the stimulus. Then they screen for all features that become uncorrelated once you condition on the remaining variables, which gives you, it doesn't work anymore, so which gives you red colored dots and blue colored dots, and I put down this schematic in the corner here. The red dots are the ones they are correlated with the stimulus, and they are still correlated even if you condition on the other stuff. The blue ones are the ones, they are dependent on the stimulus, but once you condition on the remaining variables, somehow they become independent, which is exactly the case that we have been discussing before. So this part here gives you a coloring basically where red are more direct effects and blue ones are definitely indirect effects of the stimulus S. There's an additional color that I haven't talked about so far. You can find it in the paper reference, I think, on the end of these slide sets, where we discuss all possible combinations of being conditionally independent or being dependent marginally, and these 4 possibilities. And one gives you the green button. It tells you if you try to decode brain activity, the presented stimulus from the observed brain activity, then obviously regressing out those noise variables that are not actually affected by the stimulus, but that affect the brain activity that you want to use to decode the stimulus. These green guys, they will help you. So if you train a decoding model, a classical decoding model, these variables, they will be important for your decoder to use to regress out noise. Talking about conditional independencies, that will basically be translated into the following statement. These green variables are not conditionally independent of the stimulus variable when you condition on these red guys, while they are independent if you just look at this marginally. So it's uncorrelated brain activity to the stimulus. Once you condition on the other features, they become dependent, they become helpful to decode the stimulus. So this is another thing where you can kind of see how conditional independence-based causal inference works out and actually gives you something useful at least. There's some more information that we've now gained, which I think what I've emphasized and focused on the most now is this red versus this blue color. And you're robust when doing this against hidden confounding, which is quite powerful. This is only a small subset of what you could do with conditional independence-based causal inference. But it uses strong assumptions, but these assumptions are quite plausible in this scenario. So why not use it actually and exploit it to get some cool insights? Are there any questions at this point? Yes. I will just repeat your question.
One of the statements early on today was that it's really hard to establish conditional independence from data. So how is it done in something like this?
That's a good question. So I think there's 2 answers. One is, I often hear this, and it's kind of the one point where you attack all the causality folks. If it's so difficult to find and see independence, then why do we even bother? The problem is, even if you do a classical encoding analysis in neuroimaging and you show a plot of a brain where some areas are red and some others are gray, you have interpreted this null finding. At some point you need to accept, even if there is a dependence, it's so small I cannot detect it. I'll just mark all these areas gray. So of course there could be wrongly found independencies where, had we seen more data, we would actually conclude there is a dependence. It's just a question of statistical power. But we do this, and we are quite used to doing this step and this interpretation of null findings by contrasting null findings against finding actual correlations. Does that answer that question?
I think so. Is it fair to say that you're sort of saying, if I don't find a dependence that crosses my significance threshold, then it's probably not important dependence?
Yeah. I think that's, yeah. And then the second answer to this question is, conditional independence testing is a beast. It's horrible to do. So of course this is problematic. But if you're not happy to accept this, then you're stuck with marginal dependence tests, and then you cannot say any more than just this is correlated or this is not correlated. That's just, I think it's the hard bullet that we have to accept. There's no way around this. If we continue with conditional independence-based causal inference. So that's why it's maybe fruitful and interesting to consider also different frameworks, which we will, I think, also start right now also But for conditional independence-based causal inference, you need to have ways to test conditional independence, which is tricky, and you need to have a threshold to accept there is now a dependence that, an independence, or if there was a dependence, I'm not powerful enough to detect it. But it's not something that is unique to causal inference. Yes?
Is there any reason this can't be done entirely probabilistically? So not saying something is dependent or independent, but I guess doing it in terms of probabilities.
Okay, I'll first repeat the question, so that's also recorded. So the question is there any reason to not doing it purely probabilistic? So instead of doing a hard thresholding, independent, dependent, do it in some way probabilistically. Now, as for an answer to this question,
Yeah, I think there are reasonable approaches like that. There's also a Bayesian framework to causal discovery. David Hackerman has been working on that for a long time. Yeah, the problem is they need quite strong assumptions on the priors, or they have priors of which at least I think they are not realistically. So there are lots of other issues. But still I think it's an interesting question, yeah, definitely. Yeah.
one small thing to add to this. I've not thought about this in like full detail and full length, but if you want to talk about a causal model, I think it also becomes a question of how you interpret this. Like, what does it mean to be less probable to be a cause versus this is just a cause or it's not a cause, even if it does have a small influence. So with all this causality stuff, you often end up in a more like philosophical debate about what kind of models are you actually after.
So it becomes an epistemological problem where you're introducing potentially a dichotomy. Well, in reality there is a dichotomy, but there's uncertainty in that dichotomy. You're throwing away information about these dichotomy sentences from probabilistic.
Was there another question? No? Yes.
This is a hard one, but it seems maybe an appropriate time to ask. So one of the problems in neuroscience is the idea of how the brain represents causal relationships in the world. And then that becomes a potentially even harder problem than the one you've shown here, which is you need to infer from brain activity that the aspects of the world being represented or encoded in the brain activity is encoded in such a way that causal relationships in the world are respected. Or have you thought about that? I mean, is this something you can even begin to tackle, or am I thinking that it's harder than it seems to me?
I think the question will be, is talking about how the brain represents causality, is this fundamentally a different question than asking how does the brain, I don't know.
Asking about causal interactions between brain areas, which is what this seems to be about.
Maybe that's
example.
Yes, so then it's two levels of explanation, right? So one is which area's activity does cause another area's activity. And then you're adding a complication on top.
Yes.
Is how does this represent or encode how the brain represents the causality in, I don't know, two objects in the world interacting.
Yeah, it's an influential idea. I mean, particularly in vision, that there's, embedded or an embodied causal model. But it's not clear to me that the framework here for addressing the zero order question, it would be applicable to the second order question. I don't know if you've thought about that.
I mean, it's definitely a tough one. So
I mean, it's not even clear what it means in the first place that one region influences another one. I think, Sebastian, you can comment more on that. Because of this macro observables.
Yeah, so we will have a chapter on this particular aspect, but I know that this is not a satisfying answer, but I think my take right now would be we don't even know about what you call the ground first level. It seems pretty tough to talk about the second without solving the first. But it's kind of a lame answer because that doesn't give you anything. So
it makes me feel less lonely in my confusion.
So I think from I don't know, from a causal inference perspective, it's super hard and you're just adding another level on top. So that's kind of hopeless. But having said that, the whole thing works if you put in a lot of assumptions. So if you have good reasons or you can defend against your peers that this is a good prior assumption about how the brain works, maybe you can suddenly say much more, right? So then it becomes something that we cannot decide within the framework where it's like math rules, what follows from what. But now it becomes a discussion about, do we accept these a priori assumptions, or I don't know, these insights that we accumulated over the last 40 years, and are we in agreement on what that means about how the brain works? So, but if you put in these strong assumptions, I don't know, V1, V2, blah, 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 there's a lot of knowledge, or we think we understand a lot. But if people agree and take this as a prior assumption, then based on these assumptions, there's still ways to logically consistent move on and infer certain things, right? So then it becomes a kind of, what is an assumption that you need to discuss and what logically follows from these assumptions. Okay. So you kind of shift that line. And here we've talked about things you put in strong assumptions, but on a very like conceptual core level, and then this implies a bunch of things and a bunch of ideas how you can infer causality from observed data. If you now put in even stronger assumptions, this will get you further, but you will have made stronger assumptions. So it's kind of a, I don't know, if we agree X causes Y, then we don't need to do any study, if that is our assumption. So now we've tried to push this down and be like, okay, if you find a dependence and you randomized X, then that means X causes Y. But given the assumptions, and now we observe the data, now there cannot be any more disagreement between us two inferring that X causes Y. I think this is the power of this. Once you formalize it, you can push everything that you need to discuss into the assumptions part. But everything from that point onwards, there should be no debate anymore. Otherwise, it's not logically consistent within the framework. So that's something maybe that hints at on a, like a more general message is, be very explicit about what your assumptions are, then people will generally agree much more with your conclusions given these assumptions, but maybe they will attack you on your assumptions. There's a different discussion to be had. Yes?
Forming this question as I answered, sorry. My intuition is that it's harder to do this sort of discovery of these causal relations if you're not doing atomic interventions. Is that fair? And a lot of the interventions that we can do in neuroscience often bias what the brain is doing. If we, inject current or optogenetics or whatever, we're changing the distribution, but we're not setting it to a particular value. So how does that complicate things? Like here it's easier to manipulate a stimulus and we go control over that. If I were to go in there and zap the red area in that diagram, I might not have an atomic intervention. Right? So how much harder does it become?
So the question is, we've only talked about atomic interventions, kind of you set one variable or a bunch of variables to a specific value, one value. And the question was, how much more difficult does it get if you now have interventions that bias distributions or activities to certain other distributions? There's several things. So the first is, we have only talked about what we call kind of, I don't know, perfect interventions. You set a variable to a hard threshold. So there's one trick you can do, which is kind of similar to this idea. When you have an intervention that biases a distribution, you could still introduce a node that is, am I doing this biasing intervention or am I not doing this biasing intervention? That's one trick, but I think it doesn't get you far. The other thing is you can, in the framework, incorporate or, let's say, sensibly talk about soft interventions or different kinds of interventions. So you, for example, you could, Dominik was talking about these factors and how they change independently. So let's say you have P of X given Y and P of Y, and now you change the entire conditional distribution. You're changing something about the system that makes Y translate differently into X values. You can talk sensibly about this by changing these factors. Or if you talk about functional models, you can, instead of replacing, I don't know, X equals a function of YZ plus some noise term, you can replace the equation by X equals a function of these other bunch of variables now. So there's a ways to at least formally, put formally the types of interventions you've been talking about. But then there's also, another answer is, there's also causal inference ideas or algorithms that don't need exact knowledge about what the intervention was. It's usually terms like environments, or a intervention 1 has happened or intervention 2 has happened, but you don't really know what that was. There's ideas about using this. I think the keyword would be invariant causal prediction to look up, or this independence of cause and mechanism idea. Do you want to add anything?
Yeah, one short comment that I remember a discussion in the past where someone was explaining to me that soft interventions need not necessarily be worse. Sometimes it's even better, because if you look at soft interventions, and you look at the augmented graph with this explicit interventional variable, then you can still have faithfulness, while for the hard interventions you have violations of faithfulness. So there are even some advantages. So I would say whenever you have something that has been randomized, then you are in a good situation, regardless of the details. But there's, of course, a lot of difficulties.
More questions?
Yeah, then maybe one point I would like to ask, that Sebastian's example nicely shows that interesting examples with causal discovery and causal inference are not always with hundreds and thousands of variables. So often in applications it's interesting to look at 3 variables and 4 variables or whatsoever, and do conditional independences and look at the statistics. And there's still a lot to be explored, and I'm emphasizing this because people approach me often with hundreds or thousands of variables and just say, oh, couldn't you infer the DAG? And so, well, maybe start with 3 variables. So in causality, not everything is big data. Most of the times we are doing small data, I would say. So what can be said beyond Markov condition and faithfulness? So let's say about 15 years ago, when I started working on causality, or a bit more, I didn't believe that there is nothing beyond Markov equivalence classes. And that was basically the point where I started working on that. So let's start with a little toy example. If you see this scatter plot, this is really real empirical data. And you're supposed to infer what's the cause, what's the effect. Any ideas? So is this the cause and this the effect, or vice versa? Who thinks that X is the cause and Y the effect? Who thinks the opposite? Okay, so I've played this game already several times, so I won't go to the details now. But many people really have the intuition that the distribution looks more natural if you think that X is the cause and Y the effect, because then you can think of a nonlinear function up to some noise. On the other hand, if you look at it from the perspective of Y being the cause and X the effect, then you get a quite strange model, because in this region, for these Y values, you have one cluster, here you have one cluster, then here you have two clusters, and here you have one cluster again. So when you lower the value Y, you get a sort of branching process, which would of course be possible, but it looks like a quite sophisticated process. So from X to Y looks much more natural. And in fact, X is the altitude and Y the average temperature of places in Germany. So this is the Zugspitze. It's by far the coldest place. And here you have an almost linear decrease of temperature, but if you get closer to the sea level, it doesn't hold any longer. And indeed, we have algorithms that properly classify this as X being causal and Y the effect. And this is also an example where this algorithm works particularly well. And therefore, I like this example. What's the cause? What's the effect? Who thinks that X is the cause? Who thinks that Y is the cause? Okay, okay. Who has seen this talk before? Okay. So, indeed, if you think of a mechanism from Y to X, then it's kind of linear relation up to some noise. But from X to Y, it's not that nicely linear, because the noise heavily depends on the value X. This Y was solar radiation and X temperature of several thousand days at the same place. What's the cause? What's the effect? I like that example for another reason. Who thinks that X is the cause? Who thinks that Y is the cause? Okay, there's also agreement that X is the cause, which is true. X is the age and Y the income of people in the US somewhere. And what I like about this example is that I don't know any formal criterion why we should prefer X as the cause. Yet, many people in many different audiences agree that from an intuitive perspective, X looks more plausible as the cause, which means that we have an intuition about that, although artificial intelligence, statistics, all the causality methods don't know how to infer that. So this is to encourage you also to find new algorithms. Hence, there are asymmetries between cause and effect apart from those formalized by the causal Markov condition, and new methods that employ these asymmetries need to be developed. For that reason, we have created a database with cause-effect pairs already a while ago. It's a bit embarrassing that it still consists of 106 pairs only, Here it's 105, but I have contributed another one recently. The reason is that it grows slowly, that it's not that easy to find good examples where people agree on causal structure. The idea of the website is to evaluate novel causal inference methods and inspire the development of novel methods. One method that already exists since more than 10 years is the nonlinear additive noise-based inference. The model assumption is that X influences Y via an additive noise model, in the sense that you take a function of X plus a noise that is independent of X. And here it's important that it's even independent and not only uncorrelated, because an uncorrelated model exists always. Then one can show there will, in the generic case, be no model where X is a function of Y plus a noise that is independent of Y. Even if the function is invertible, the proof is non-trivial. So note, a function Y can always be written as a function of X and a noise term if you have a function with two arguments. But what is special is that the noise is additive. So when the noise is additive and you require the noise to be independent, then it heavily restricts the class of P of Y given X. And the intuition is the following. An additive noise model from X to Y imposes that the width of noise is constant along X. So if you move here, then you have always the same width. And if the function is nonlinear and you look at the noise along Y, then it changes its width, so the variance or changes across different Y values. The causal inference method just reads, prefer the causal direction that can better be fit with an additive noise model. And the implementation is you compute a function f as nonlinear regression by any off-the-shelf machine learning algorithm. And you compute the noise as the residual term, just y minus f of x, and check whether this noise is independent of x. So you need a test that is able to account for higher order dependencies. And this definitely performs better than chance on real data with known ground truth. And if you decide only in those cases where in one direction it's reasonably independent and in the other one it's reasonably dependent, then you can increase the rate of right classifications up to, let's say, 95 or even a bit more %. This is the evaluation. So if you enforce decisions, you have about 75%, but if you only decide in the most obvious cases, you get much above that. But there's sometimes a misunderstanding about the method. We don't claim that every causal influence can be described by an additive noise model. We only claim that if there is an additive noise model from one direction but not the other, the former is likely to be the causal direction. And this is related to this ICM, this independence principle, in a nice way, because the argument is if nature chooses P of cause and P of effect given cause independently, it is unlikely that the result is a joint distribution P of effect cause that admits an additive noise model from the effect to the cause. So it's just unlikely to get an additive noise model in the wrong direction. And to back this up by a bit more math, this is a slide showing that if let's say you have an additive noise model from X to Y. Then you can show that the distribution of Y and the distribution of X given Y are related by this differential equation, which means if you know that one, then that one is basically determined up to one simple degree of freedom. So P of xy almost determines P of y, which violates the independences. So we reject y given x, provided that P of y is complex, because we assume that nature chooses these objects independently. And I've justified that via algorithmic information theory in a longer paper. But I don't want to go to the details here. Yeah?
Does it matter what distribution we sample n from? Does it have to be uninormal and Gaussian, or can it be
no, it just needs to be complex enough to make this argument work. So, yeah, Gaussian is always bad for all these arguments. And, uniform is a bit better, yeah, but still bad. You need complex distributions, because then you can argue that this object contains a lot of information about that. I mean, in the linear Gaussian case, the argument must fail. And the reason is that there is just no information in these distributions. Another causal inference method that is basically just a nice fairy tale, so it's not a method that you would use in practice, at least not in this form, in the form I'm presenting it here. We basically use some method that is related to this one in practice, but that's another story. So this is just something that is nice to explain the independence of causal mechanisms. So assume you have a deterministic relation between a variable x and a variable y, and you are supposed whether y is equal to f of x or x is equal to f inverse of y is the right causal model. And the idea is that if x causes y, then f and the density px are chosen independent by nature. So, which means that the peaks of p of x do not correlate with the slope of f. And you can show that if this is the case, so we have a reasonable formalization of the statement, then you can show that in the backwards direction you observe a correlation between density and slope. So just to explain that here, you have a density here that fluctuates some way. You have a function that has nonlinearities with larger and smaller slope. Then the regions of y that correspond to small slope of x tend to have higher density. And for that reason, p of y tells you something about the function. Unless you have adjusted, you have fine-tuned p of x in a way that it doesn't. So for typical choices of p of x, independent of the function, the regions with low slope tend to correspond to high density of y. And for simulated data, you can show that this is a causal inference method that really works for all these deterministic models. We have a version for time series, linear models in time series, that is in the same spirit and pretty much related to this principle. And that also worked for real data, for the limited number of data sets that we had. Okay, some questions on that? Yeah? Yeah?
At some point we kind of lost the notion of doing
Yeah, yeah. Why did we lose that? Yeah. Okay. Yeah, good question. So let's say the first part was about how you use the DAG, if you know it, and the second part is how you get the DAG. So how we use it is just the first. Yeah. Okay?
Actually related. So when doing, do we need to add new data into the DAG, or you're just using the existing?
If you add new data to the yeah, I mean, basically, you could say you change the DAG because you cut the relations to the parents, and this way you also change the distribution. So in a way, it's a completely different data set. So this is also why it's not really a statistical problem. So statistician can't conclude anything for the interventional setting. Yeah. Okay.
So that case in particular, it only works when the UX is uniform, or for example?
No. Yeah, good point. Good point. Maybe the drawing is a bit misleading. So it's not at all. So you can have many fluctuations. So the only requirement is that they don't correlate with the slope. So sometimes you have high density in regions of small slope and sometimes in high slope. We have formalized that. You can, maybe I should write it down just to show that it's that it can be formalized. The formalization is the following. Let's say we have a function on 0, 1. So this is the simplest toy model. Just the bijection of 0, 1. And then if you postulate that integrating, oh shit. Can you hear me without microphone? So if you integrate the logarithm of the derivative with p of x, it should be close to integrating the logarithm of f prime with a uniform distribution, which is just saying that the fluctuations, the high density sometimes meets low slope and sometimes large slope. Why logarithm? It's just because using logarithm, you get some nice information theoretic interpretations of this principle, and therefore it generalizes well to other settings. And then you can show if this is the case, then you get a positive correlation between slope and density in the backwards direction. Okay? Further question? Okay, I think, Sebastian, it's yours. Yeah. Oh, yeah.
Okay, so we have 5 minutes until the break. I think it might be a good idea to not rush through this now. Maybe I'm going to try to give a summary on a high level, and then we can check in whether we are all on the same page. So we started off with why causality. One claim was basically a lot of questions that we ask are about causality, so we should know how to infer causality. If you don't care about causality, fine, you don't need this, but a lot of statements, they kind of implicitly talk about causality, and then we need to talk about this. Starting from there, the idea was let's first formalize, if we have a causal model, what would that mean? What would it look like? How would it be doing different from seeing? how could we evaluate certain do statements from a given causal model. That was kind of the first part. And then I think we made this harsh transition to causal discovery. So we are rarely in a situation where we're given the full causal model. I mean, systems where we know the full causal model, probably we're not going to investigate them any further at that point. So we are much more interested in the causal discovery part, which we talked about. The first point on that topic was conditional independence-based causal inference. So here the idea was, if you can write down structural equation models, like functions that relate parents to childs, and you know which conditional independencies that implies in the observed data, and you make the additional assumption of causal faithfulness that all these conditional dependencies are all the ones that you will observe in the data, which could loosely be translated to something that, like, there is no fine-tuning of parameters so that paths unexpectedly cancel. If you make these two assumptions, then you can, by looking at the conditional independencies in your observed data, infer something about the causal graph. Then we talked about a special case where we randomized the stimulus in this neuroimaging study and only looked at 3 variables plus these 2 assumptions, and we could infer something about cause-effect relationships between X and Y in the brain. Then I think we talked about also the potential outcomes framework at some point, but we only did this in passing. And then the motivation was we need assumptions to do causal discovery. And now we've replaced or talked about different assumptions. Instead of talking about all the conditional independencies in the graph are all the ones with a Markov and faithfulness assumption, we replaced this assumption, or we were trying to look for different assumptions that could also enable us to infer causality from observations. So the first assumption was this additive noise model that we discussed right now. So if you assume that is the model, what could you possibly infer from observed data? Could you decide between the 2 directions? And you can. And then there's this note, an important remark. You don't have to claim that all the relations are actually additive noise relations, but it's unlikely that you will find this asymmetry between the 2 directions in the non-causal direction. And then we talked about the special case with a deterministic causal relationship, I think. And then next would be on inferring causal structure via independent component analysis. And I think this is what we will start with after the break. So now I would ask for kind of more general questions, or where you got lost, or what we should maybe repeat or expand on in the second half of the course. If there are any questions, comments, criticism, let us know. Okay, plenty, good.
I was just wondering, are there any ways to infer bi-directionality? So far it's been A plus B, but how do we know A plus B and B plus A?
Very good question. The question was about bi-directionality. It's one of the classic questions. There's kind of a standard answer that I use to kind of sidestep this question. So I'll first give this one. What truly is a bidirectional causal influence? Maybe oftentimes, and I believe most of the times, it's only the case when you haven't resolved in time your model properly. What do I mean by that? Maybe instead of talking about X causes Y and Y causes X, we should be talking about X at time point T causes Y at time point T plus 1, and Y causes at time point T, Y at time point T causes X at time point T plus 1. But these are 2 different variables in that model. So that would be one response to this. You can show that if you have time evolving systems, so we will talk about this in the second part, and you only talk about snapshot data, so stationary distributions basically, you will need to write down bidirectional arrows in this graph. But there's a lot more to do to actually properly conceptualize what it means to talk about causal relationships in that case, because what does it mean to set a time evolving system variable X to a certain value? Do you clamp it to that value for the entire time? Do you just once knock it off and kick the system and then let it equilibrate again? So there's a lot more to be, I don't know, make precise to actually talk sensibly about bidirectional causality. And then if you don't go with me and don't like all what I just said, there is stuff and people who focus about basically inferring not DAGs, not directed acyclic graphs, but different sets of graphs where you can have bidirected edges. But for me, conceptually, I already get in trouble with the notion of a true bidirectional causal relationship. But there can, I think this is a good topic for like debate and opinion. So if
you can find papers of Joris Moy, for instance, and Jonas Peters also.
Yeah.
It just strikes me that it's a system of coupling differential equations. I mean, that seems to be a system of bidirectional causes, and these are not finite. Time is not finite. I mean, continuous time systems describe the world really well. So that your workaround may not apply.
I fully agree. Yes, it may not apply in my workaround. Differential equations are, the name again you need to look up is Joris Moy. He discusses this, how you can sensibly talk about causality when you have a system described by differential equations. Because I think so far we kind of took a path where it's easy to think about what it means to intervene and what the system actually is, because we're kind of on a more macro level. If you have differential equations, even the concept of what it means to intervene is a bit more tricky to actually formalize. But true, then you can have bidirectionality of some form. So bidirectionality, I would just say, is a topic of debate and is a problem, but maybe, I don't know. Is there any?
Yeah, I mean, some of these papers discuss, for instance, the equilibrium states of these differential equations, which can have bidirectional errors. So, also in one paper with Joris Moy, for instance. Yeah.
So I think kind of the trick with this kind of stuff is once there's time, you need to be really, really precise about what you're talking about when you talk about an intervention and the distributions. Is it the stationary distributions that change once you intervene on X? Is it the differential equation that changes? So then it becomes a really important step to clearly define what you're actually after. Yes?
How do you expand the additive noise model to multiplicative noise model? Because for neural processes, that would be more interesting.
You mean kind of taking the logs and everything works kind of idea?
Yeah, if this approach works.
I think it's something we've always put on the long side, kind of. It doesn't trivially extend. I think that's...
Yeah, I would say almost all of these classes have identifiability because, I mean, whenever the class doesn't cover the set of all models, then it's unlikely that you get such a model in the backwards direction. But having said that, whenever you extend your class in models more and more, then identifiability gets weaker and weaker. So you will always find one of your models that also works in backwards directions. So it's hard to say where is the right trade-off. I think there are some limitations.
Yes.
Is there also a role for model complexity? It seems like most common things are in daily lives and just simple models. With the graphs, for instance, instead of a deterministic relation and it's just a monotonic function, it seems like an easy way to causal thing is typically a simple relation. But I'm not, is there anything that can be formalized to that? Is it a good heuristic for?
It's a good heuristic. I have been claiming that since years. I've been trying to formalize that since years, and yeah, it's hard. I mean, it's hard to find the right notion of complexity.
Any more questions? Otherwise, I think this might be there's one more. Okay, we take this one more.
It might be something you're covering later on, so if
Yep.
that's the case, that's great. What about interventions that you can't take? Like, you can think of plenty of, distributions and variables, random variables that it would be not, I don't know, the smoking case. One of the classic examples, I think, is the fact, well, you can't get people that smoke for 20 years to find out whether that's good or bad, like for cancer. But probably, there's something that you might know about later, like, there must be a way that works around.
So the question was, what if there's interventions that you cannot perform? But I think it was two questions. One was, what if you cannot perform this intervention because it's ethically problematic or very expensive to do? Then hopefully some of our tools can, by making other assumptions, help you to infer the causality. There's another more fundamental question to this is, does it even make sense to talk about certain cause-effect relationships if this quantity or variable that you're talking about doesn't have a proper interpretation, or you wouldn't even know what it means to intervene?
Yeah. How do you change the age in the age income scenario?
And this is a more fundamental or conceptual problem, because then people discuss, and this is still an ongoing debate, does it make sense to include the age variable in your graph if you cannot intervene on it? Is it sensible in some way, or should you just remove that variable and be like, age is not a variable that I can intervene upon? And then I give you one more preview, and then I think we're off for the break. This is why one fundamental point we're raising is you need to specify your question and the interventions you are possibly interested in. So in that case, I would say if you're modeling a system and you a priori know I'm not going to intervene on age anyways, then just remove it from the set of interventions you're interested in. That will play a role later. Okay. Then, sorry, now we're 10 minutes late, but enjoy your breaks. Before the break, we started talking about different assumptions that we could make to make causal inference work or causal discovery work. Now we're going to talk about the relationship between ICA, independent component analysis, and inferring causal structure. And there will be certain assumptions that we will need to make, namely we will assume a linear model, non-Gaussian noise, and acyclic causal relationships. I'm not sure which way around is best to ask the question, but who doesn't know about ICA is not afraid of openly. Okay, everyone knows about ICA, that's good. Okay, ICA, independent component analysis. I'll talk about what that is and what it does as I go, so you shouldn't actually worry if you don't know yet. Let's start with a linear acyclic structural causal model. I'm using this vector notation for now because it will simplify everything that follows. But think of these x1, x2, xd components as being the individual variables that we're talking about. Then this model says each variable is a linear function of x2 up to xd plus some independent noise. So the acyclicity here is reflected in this lower triangle being all 0. So I've just ordered the variables in a way that I don't need to put any values in the lower triangle. That I can do only because it's acyclic. Acyclic meaning I don't have these bidirectional issues. If that is the case, that doesn't work anymore, so I'm sorry. So I have this, sorry?
Should those be x's on the left-hand side?
Yes, it should be x's on the left-hand side. Because none of the x's on the left-hand side is a function of itself. That's ensured. So the diagonal is also a 0.
Okay.
So it's ensured by the design of this B matrix that it does actually make sense and work. Okay, so we have mutually independent component S1 up to SD. Mutually independent means any pair and any combination of those, they are independent noise variables. And this is closely linked to independent component analysis. So independent component analysis aims at solving a very similar or related problem. So let's rewrite this in matrix vector notation. So this is the x1 to xd components stacked. This is this B matrix with these certain properties. So we need all the lower triangle values to be 0. And then this is the vector of noise variables. And now we do a simple reformulation. We bring B times x on the left-hand side and multiply by the inverse, and this is what we end up with. So this is the identity minus this B matrix inverse. This is sum matrix times independent, we call them source components, and they give rise to these x variables. This problem here is basically what the ICA model or algorithms try to resolve. So you're given these mixed distributions x, you assume that it's a linear mixture of independent sources, and you try to revert this mixing to get back to your s variables on the right-hand side. But now we've basically converted this linear acyclic SCM that we started with on the top into something that looks pretty much like ICA. So can't we use ICA to solve this causal inference problem? And we can. So the methods are called linear, non-Gaussian, acyclic models. So this is, the assumptions in here is B needs to be this lower triangle thing, which is the acyclicity. The S components need to be non-Gaussian for reasons that will pop up later. And it's linear because it's just the product plus this additive noise. So now we can identify B in 2 steps. The first step is we infer identity minus B up to scaling and permutation using any off-the-shelf ICA algorithm. So we use a method that can resolve this. For this, we need non-Gaussianity. I will explain you on the following slide why this is the case. So this is why we have this assumption for the original causal model. If we don't assume non-Gaussian noise, then it doesn't work because ICA doesn't work. Once we are happy and have our identity minus B matrix, we actually want to get back to this B matrix. So we will try to resolve the scaling issues and the permutation issues that are left once you do ICA. You still cannot decide on the ordering and the scaling of the variables. So we try to resolve this to obtain a B matrix, which we can do. But for this, we need the acyclicity. So if you assume your B matrix is of this form that all the lower triangular values are zeros, then you can actually resolve the ambiguities in scaling and permutation. So why do we need the non-Gaussianity? Here's a simple example with only 2 variables. It's a bivariate Gaussian case. And I will talk about the indeterminacies of ICA. So if ICA fails, this whole thing can't work. And ICA fails if there's only Gaussian noise. Why is that the case? If we have this bivariate Gaussian, this blue scatter plot here, we can model this 2 ways. One is we can, it's written here, we can model x as being a normally distributed variable and then y being a linear function of that plus noise. That should be the red line, and then the green line is you model the y as an independent noise term and then x as a linear function of y plus additive noise. So if the noise is Gaussian, you can model this both ways around and there's no way you can disambiguate the 2. More formally, why does it work if we have non-Gaussian distributions? So there's a nice theorem that kind of lies at the heart of this method to work. So we start with these 2 dependent variables, and then the statement is the joint distribution over x and y admits a linear model in both directions. So that's what we want to avoid. It does so these are the 2 models in 2 lines, if and only if the distribution is a bivariate Gaussian. So as soon as it's not bivariate Gaussian, we are fine. It can only be in one way. That's why all the variables being Gaussian noise wouldn't work. If it's non-Gaussian, there can be a linear model in at most one direction. And now under this linear non-Gaussian acyclic model class, the causal direction is now the one that admits a linear model. It can only be one of the two directions. Now you scale this up to your D components, and then you can actually make this work. So let me go back to that slide first. So we can identify this model. So we can identify B, which tells us everything about how the X variables causally relate to one another under these assumptions. Now the question is, can we go any further? Because it's really restrictive to have independent noise on all variables. And also non-Gaussian noise on all variables. So I'm going to present an extension to this where we're trying to squeeze out a little bit more. We start with a traditional model up here, where the S has mutually independent components, and we're trying to add in some more stuff. So we have a confounded model. We have the original model plus some confounding term H. And I'm not making an assumption about H having component-wise independent sources. So H is not component-wise independent, but it's group-wise stationary. That means for a certain bunch of samples, the distribution of this H is the same. So you might think of, you change the entire environment for a subject, or you turn on a different amp or something like this. But within one of those sessions, these H values have the same stationary distribution. If you make this assumption, you can incorporate some confounding terms. So how does it look like? You do this step here, this reformulation, you get back to the classical ICA model. If you do the same reformulation here, you end up with this. The problem now being, up here, it was a linear combination of S, and S was component-wise independent sources. Now it's a linear mixture of independent-wise, component-wise independent sources plus this confounding term. So classical ICA won't work. We need something that adjusts for this H. And that's what we've basically done with this confounding robust ICA. It doesn't adjust for any confounding. It adjusts for this type of group-wise stationary additive confounding. But at least you can do this. If you have sensible reason to believe that this noise class covers a lot of your noise, then definitely go for it. If you do so, now this confounding robust ICA allows you to identify even a confounded linear Gaussian, non-Gaussian acyclic model. It accounts for dependencies due to H if H is group-wise stationary. A whole bunch of talk just to say that we can adjust for some of the confounding, but it's really important because oftentimes we know nothing about this confounding. And assuming there's no confounding is much stronger than assuming there is confounding, but it's group-wise stationary. I'm happy to accept it's group-wise stationary noise. We've applied this to EEG data, but not so much talking about the causality part, just as a confounding robust ICA. We've also applied this to climate data, because instead of strictly requiring group-wise stationary noise, you could think of H changing really, really slowly over time, compared to S changing really, really fast over time. Then in a reasonably sized time window, H appears to be group-wise stationary, almost, but S is not, and group-wise independent, and then you can resolve this whole thing. If you want to read up on this, I would refer you to the paper, because it would take up far too much time. Yeah.
What would H be in your EEG?
In our example, we use basically H to account for subject differences. So if you put a subject in this, under the cap, slightly different electrode positioning, slightly different brain, slightly different room setup. Of course, it's not all group-wise additive noise, but at least we can account kind of for the first order changes between subjects. So I think in EEG slang, it would be we have a group ICA. And we claim it's a more principled group ICA than just stacking the data into one long concatenated thing. Yes?
So, if I understand this method of deducting to ICA, it allows us to think about if I have like a linear relationship and the group noise is non-Gaussian, then I can infer which direction that must go. My question is, what happens, how well does this transfer to relationships which then are non-linear?
So basically on paper it fails. In practice, if it's close to linear, you would still get something reasonable. I'm not sure, so I think the key thing we would need is something that tells you the B matrix that you got out is definitely not the one that you're after because there was nonlinear effects. But you can basically check, so at least for the, let's go first for the classical ICA model. If you identify this B matrix, but even after inverting the linear mixing, your sources still look dependent, then of course it didn't work, right? Your ICA didn't actually spit out independent sources. So you have kind of a way to detect the failure mode. Here it gets a bit more tricky because you don't get actually independent sources. So even if there's dependencies, you would need to look deeper whether the dependencies could be explained away by some stationary confounding term. But you would need to do kind of model checking afterwards, yes.
I'm missing what we learned about causal relationships from this model, but where does that come in again?
Yeah, it's kind of hidden away, I think, on this slide, where I stacked all of this matrix notation thingy into just one matrix X. But if you have the B matrix, you know all of these structural equations. You know X1 is an effect of X2, X3, X4 up to XD with these certain weights. So when you have B, you have everything, kind of.
But it's the upper triangularity that implements the assumption of causal interactions or causal relationships.
Acyclic causal relationships, yes. So it might sound a bit strong to assume this thing about this B matrix, but it's just the acyclicity. And I mean, of course, acyclicity is a thing to be discussed, but you just, if it's acyclic, you can always permute it into an ordering of the X variables so that the matrix satisfies this condition. So you would need to relabel. So if you realize your matrix is not upper triangular, then you would find the permutation that makes it upper triangular by relabeling your variables. More questions on this? Okay. So again, to keep in mind, there's different assumptions that we made, and then we try to resolve the discovery problem by exploiting these assumptions. Here was these assumptions that actually go back to the ICA algorithm. So if any of you can solve the ICA problem for more general classes, that would also automatically give us a broader class of causal models that we could infer here. Okay. That was the discovery part. So if there are any questions for discovery, now is the best moment to ask, but later there will also be a good moment. Yes?
Trying to see if I'm getting that intuition right here. So the idea is that starting from a model like ICA, which is traditionally seen like in statistics as correlational in nature, then we can still make causal claims under a certain set of assumptions.
Yes. Okay. Maybe the starting point might be different depending on which community you're coming from, but yes, that's kind of the idea. Okay, now is a slight shift. We talked about discovery, but there was a bunch of questions about what about bi-directionality, what about time series, what about whatever, all of these things, and this is what we're going to cover next. There's a lot to be discussed about macroscopic versus microscopic causal modeling. So basically anything that we do in neuroimaging is on a macroscopic level. In neuroimaging is super pressing. That was the original motivation for me to look at this on a methodological side, is you don't even know what the underlying model is, nor do you know the transformation of this that you're observing. So you just are given these observations, and now you want to sensibly and reasonably talk about voxel activities causally influencing each other. So from a conceptual standpoint, there's a lot of discussion to be had. Why does this even make sense? Like, what does it mean for a voxel activity to cause another voxel activity? You're observing only some weird transformation of some actually fine-grained underlying, I don't know, atomic or even subatomic level model maybe of the world. So how does that make any sense and have meaning? That's what we're going to cover here. So what I just said is we can have fine-grained and coarse-grained models. For example, we can talk about a disease on the molecular level in one individual. We can talk about entire individuals and how the disease spreads throughout the body, or how it spreads throughout countries. And we ideally want to do this in a causal way. So we here maybe want to talk about which health policy intervention we should perform, or here we want to find the best treatment for individuals. But all of these levels, they need somehow to consistently relate to one another. So maybe ideally you would hope if you have the finest level by emergence, the coarse-grained questions can also be asked. For example, traffic. For one given cross-section, how should you time the lights to have best traffic throughput? How should you do it on a city-wide or nationwide or continental-wide level? So the topic and question of this part is, how can we relate these different levels when we talk about causal modeling? To give a motivation why it's important is to look at the failure. What can go wrong if going from micro to macro was done in an incompatible or inconsistent way? Let's consider this long-standing problem. How does diet affect heart disease via low-density lipoprotein, high-density lipoprotein in the blood? And by now, there's kind of a consensus that the LDL is the lousy one. It is bad for your heart disease, and the happy DL is kind of good for your heart disease. So nowadays, we're kind of happy to draw this graph. Your diet influences both, and both have a different effect on heart disease. What we're claiming here is that the long cholesterol wars, so there's books about this whole thing that went on for 20 or 30 years, can be viewed or explained partially by there being an inconsistent transformation of an underlying level that took place in the past that we first needed to resolve. So what do I mean by that? Back in the past, we could only measure total cholesterol. If we want to talk consistently about how total cholesterol affects heart disease, we will run into a problem depending on which particular diets the different studies used to implement a change in total cholesterol. So you find 10 studies that tell you total cholesterol is good, 10 studies total cholesterol is bad. That's only because you considered the sum of LDL and HDL, and you run into a hell of a lot of problems. So basically, if you incorrectly transform a micro level to a macro level, that can be problematic. The example I've given here is you were given in the past this transformation unknowingly because you could only measure total cholesterol. This is one question you might ask, but also it could be that you have a model at hand and you want to simplify it or reduce dimensionality, and you want to do so in a way that preserves causal reasoning. You don't want to do this if you lower your dimensionality, because suddenly your causal model lost a lot of its capabilities and meaning. Another example is EEG as an example where, let's say for now these cortical sources are causal variables, so cortical sources can affect one another, but we are only given a linear mixing. And I think by now everyone agrees that it doesn't make sense to talk about activity at electrode 1 affects activity at electrode 2, at least not when we're trying to talk about the brain and how areas affect each other. Because if I talk about this on the electrode level, every electrode measures a superposition of all these cortical activities. So how does it make sense to say, if you change the signal of that electrode, you would need to change all of the activity in the brain. So obviously you would affect all of the other electrodes. Or another way to view it, that was how I was first challenged with this problem, is why don't you just flick out one electrode and then wonder what's the effect of this? This will be an intervention on the electrode level, but we don't actually want to talk about the electrode level. So also here we're given observations of a transformation, but we want to talk about the underlying level. That's basically why we're doing all of this source reconstruction, independent component analysis, maybe to get down to these causal or cortical variables. Okay, so that was for the motivation. The question from a methods perspective is, how can I turn this causal model into this causal model without losing causal meaning? So I just realized actually there's another benefit to these slides. They give you a different viewpoint on what a causal model is as opposed to a probabilistic model. So if you were wondering all along what the whole fuss is about, here's another angle to look at this problem. A normal probabilistic model gives you for each parameter setting a joint distribution. That's all that it is. A causal model gives you more. It gives you for each parameter setting a set of interventions, namely for each intervention that you could perform on the system. So you have parameters, and then you can do interventions, and it gives you a set of distributions. So the whole trick and the whole struggle with causality is you're often given only observations of this, but you want to make claim about this and this red bit as well. That's why we need the additional assumptions. So now I've basically introduced the viewpoint that causal models are posetsets of distributions, and I will explain the posetsets because it's important to realize that it's partially ordered sets of distributions, not just a set of distributions. So I've put down as an example 4 distributions here. By this notation, I mean it's the distribution over all the x variables, given I haven't performed any intervention. This is the one, let's say, over all the x variables when I set a to 0, when I set c to 0, or when I set a and c to 0.
So is P null just a joint distribution?
The observational joint distribution. And the others are also the joint distribution, but when you have performed these interventions. So now that I put actually names and variables into those do operators, you can realize there's some order to this. And the order is as follows. If you start from the observational setting, you can of course perform the intervention to set a to 0, or you can perform the intervention to set c to 0. But when you start here, you cannot go from c equals 0 to having performed this intervention to doing a equals 0 directly. So there's some structure to these interventional distributions. And that is basically why we say a causal model over the x variables implies a poset of distributions, poset for partially ordered set, which tells you there's a bunch of joint distributions, one for each intervention, and some interventions are less or equal than another, or they come before another intervention. So the intervention do a equals 0 is less or equal than in the intervention do a equals 0 and c equals 0. That whole talk about this partial ordering structure, that is important because we believe this partial ordering structure is something you want to preserve if you transform your model. There's counterexamples why you don't want it, but they're a bit intricate, so we can discuss it maybe after this tutorial if you're really keen. For now, I would hope you could just believe me for a moment that if you break this, the whole causal terminology of these models seems to be really upside down. So we want to make sure this is being preserved. What do I mean by that? So let's start with a fine-grained X-level model that's on the left-hand side. Let's assume this was our LDL and HDL example. But back in the past, people have observed only a transformation of these distributions, namely the sum of LDL and HDL as total cholesterol variable. So these are the ones on the right-hand side. This is the transformed causal model. And now in the example that I put forward with the total cholesterol, this transformation was inconsistent. The aim of this game and of this work is to characterize when is a transformation good for causal reasoning and when is it bad. So when is there a structural equation model on the Y-level model that is consistent and reasonable to talk about with the lower level model? The LDL-HDL example was an example where this transformation didn't work out. So we want to see when does it work out. So what do we want to ensure? Let's say we have a time-evolving system, but we only observe the system at a certain point in time. So we only take snapshots. So our transformation is basically, there is an underlying causal model on the x level that is time-resolved, but we are given this transformation just by our mere inability to observe the system at every time point. So we are only given this transformation, we only observe these time shots. We want to make sure if we intervene on the a variable and set it to a particular value, that in this simplified or transformed model on the right-hand side, this corresponds to setting the one a variable to this value. You also want to have this the case for if you intervene on the c variable over time, and also if you intervene on both. So you want to make sure you can kind of sensibly talk about this. And we've seen a case where we couldn't. So we want to preserve these compositions and that interventions meaningfully translate between those two levels. This is the math behind it. I'm not going to go into detail. Basically what it says is if you have a fine-grained model and a coarse-grained model, they're related by a transformation, then this is causally consistent. If for every distribution in the fine-grained model you can find a meaningful coarse-grained distribution, and all the interventions translate in a meaningful way. You don't want to have the case where intervening on total cholesterol could mean two things on the lower level side. And then what it basically means in math to be causally consistent is, you can see here, the upper level is the x level, which is the fine-grained model, let's say, and the lower level is the y level model. The cool thing now is that it's consistent, which means for each arrow on the top, there's an arrow on the bottom. So these two guys having two models on two different levels, they can meaningfully talk to each other and be like, hey, I've set this whole brain area to a certain value. And the other guy can say, okay, you set all these 5 to these particular values, and they can do it in a meaningful way so they would come up with the same predictions. That was the whole aim of the game. Now, some more down-to-earth examples where it's important. You can show under which situations is it now possible to marginalize out variables. And that's really the backbone of everything that we do, because we throw away a lot of variables outside the system, that go in the system or that go out of the system, and in between nodes that we actually observe. And we can characterize when you can do this. So these 3 different colors here basically tell you you can marginalize out children that don't go back into the system. Okay, that's kind of trivial. You can marginalize out variables that just go in the system. And you can marginalize out these on a path, along a path variables. That's cool, and that's good news, because it means we can sensibly talk about a subsystem of the world in a causal terminology. We can also do these type of transformations. We can have a bunch of variables on a low level, and we can sensibly talk about averages, let's say, of these variables. And then this is the most important for time-evolving systems. We can also talk sensibly about equilibrium distributions or stationary distributions of those. But we can only do so under very certain restrictive assumptions. Are there questions? Yes?
Just to check my understanding, when you intervene on a coarse-grained variable, is that the same as saying I've intervened on all the subparts such that they have this total value?
Yes, plus that was exactly the question that we needed to kind of conceptually resolve. What does it mean to intervene on, I don't know, the number of people in that room? Like, can I sensibly talk about this, or would I need to go down and say, I've put this person on this seat, I've removed that person from that seat? And when can I sensibly do this? And basically, it's a modeling choice. If you want to talk about the intervention, I put Dominik on this very chair, what's the effect on, I don't know, our mood? Then I need to model this very individual intervention. Then I cannot talk about, okay, I set the average number of people in this room to 10, because then this is not covered as a special case. But maybe I'm not actually interested in that intervention, so I'm happy to say I'm ignoring that intervention, I'm removing that from my modeling abilities. can I now sensibly talk about the average number of people in the room, how they affect the temperature next door, or something like that. And the goal here was, how can we conceptually formalize and grasp what is possible, what is not possible, what macro properties do make sense to attach a causal meaning to. And probably you're all convinced by now, it's not actually trivial to talk about macro properties in a causal language. So that is what pops out here. Okay, that was a short, yeah.
It would be helpful, I don't know if it's easy to do, can you give an example of a transformation from a fine to coarse-grained scale that would pervert the causal relationships so that they're not inconsistent across these levels? I can't come up with one.
Okay. Yes. Okay, so the question was, can I give an example of where a transformation leads to a kind of perverted macro causal model that doesn't really bear any sensible meaning? That is a very good question. That was the question that we were asked also for the reviews and what we were challenged for the most. So there is examples in our paper, but to people they seem like super contrived. Now there's two ways to respond to this. One is they're so intricate, so everyone agrees this is something we want to avoid. So here the challenge was, what is the core minimum requirements that we need to establish to rule out these intricate cases. On the other hand, when you put down these counterexamples, you realize it's really, really strong assumptions that you need to make it work. So, for example, let's say this is an example where averaging works. The example that we show in the paper where it works is only if every single edge from the x level variables on the left to the right has the same weight. You can show whenever one of the weights is different, it doesn't work anymore, because if you set the value of the x variables on the macro level now, you're only talking about, let's say, the average value. You could implement the same average with a lot of different values on the micro level. And if one of these edges is really an outlier, let's say one has a super high weight, as soon as you put a little value of the average value on this variable, your distribution of the set average will look very different from not doing this. So this is one kind of case where it's perverted. I'm also happy to give kind of an idea on the blackboard of what could go wrong, but the intricate cases, I'm first going to tell you what happens if you do it. So we have a simple example where you have x1 causes y and x2 causes y, and you transform this into a model where the sum of x1 and x2 causes y. You can construct a case where this transformation leads to the following problem. If the guy on the simple model talks about not intervening on the system, the guy on the macroscopic side would also agree that it's not intervening in the system. If now the micro-level person implements an intervention on both variables, that would mean the macro-level guy sets the sum of those two variables to 1. So that still works. And now you can construct a case where the macro-level guy just flips the two values, so the sum is still the same, but the guy on the macro-level model cannot represent this because the distribution now has changed. But he has only this one intervention performing ability on the sum of those two variables. So then he cannot sensibly talk about setting the sum of those two variables because there's two ways to implement this. This is kind of the perverted problems you end up with. It's really hard to describe. Like, there's a lot of failure modes, there's a lot of things that don't work and do work. I think the core take-home maybe is you need to specify what interventions you care about, otherwise you cannot do any transformation or simplification. So that's the first really important take-home. So, I don't know, if you want to average 100 variables and 100 variables, then unless all of the edges have the very same effect, unless this is the case, which is a really strong assumption, you cannot just take the average of those variables, because then there will always be one intervention that you cannot represent. So that's one. You need to throw away interventions. And then the second one is this kind of idea of homogeneous effects or something. That helps, but it's only an intuition. Like I mean, this is for the averaging case, but if you talk about time series, it's not at all clear. If you look in the paper, basically we can show that the abstraction works if you have identical noise over time. Identical meaning all the same value throughout the entirety of time. As soon as you add Gaussian noise, it doesn't work anymore. So why do we even hope to be able to talk about these guys here causally if we cannot make this work conceptually as an abstraction from a lower level? So that's kind of, it's a big problem. And then the next step is, can you sensibly talk about when this approximately works? So when does it make sense to talk about this? It doesn't exactly match all the distributions, but approximately it's okay to use this high-level macro model. And there's work on this where you can reason that you do, the error that you end up with by looking at this very simplified model can be bounded under certain conditions. And what it gives you on is a handle on, are you happy to assume the micro level behaves like this? Because under these assumptions, we could potentially talk about the stationary distributions in a causal way. And it gives you clear criterion to reject even the idea of modeling this causally. That's kind of where we're heading at with this. But yeah, it's a big problem to get a good intuition about when does it work. But we need to know when it does work. And so basically both of your questions were pointing at where we see the strong point of this very abstract formal talk and framework. You can now ask the question very precisely, at least. So let's say you assume a certain type of model on the micro level. Now you can look at this framework and say, okay, if you only observe snapshots, then this is the type of model class I need to talk about on the macroscopic level. Otherwise, it doesn't work. Or if you're given the transformation and you say, I want to take averages, then I can explicitly tell you, okay, you cannot do this, this, and this on the micro level. Otherwise, you cannot take averages. So it kind of is now a way to explore the realm of possible models. That's why it's cool, but it's very abstract at this point. More questions on this?
Just make like a concrete example. So, as mentioned, we have a Newton study, and we're recording activity in an area, and we want to infer whether there's the activity in that area as a causal effect on a behavior. And we were just measuring an average over, like, on a microscopic model, we have all the neurons in the area, so we just have averaging like a bunch of neurons. So, like that, does that mean that we can only make that statement if we have our transformation from the microscopic model to the microscopic model, so that all neurons contribute equally to the effect, but have the same weights to the modeling?
That's a very good and very important question. So, okay, so I think there's several ways to answer this question. One is, the way you phrase the question is, we want to talk about how does this brain activity cause the response. So, I would say just write down any model. You cannot falsify it anyways because you cannot intervene on this average, as of now at least. So if we cannot falsify any of the compatible models, then we cannot disambiguate between those two. So that kind of the very destructive answer is, then this question isn't even a meaningful question, because you're asking about causal relationships between variables that you will never intervene upon in this way. And it's very destructive. Another way to answer is, if you hope that in the future there will be a device that can set the average value of variables to a certain value, then that's cool, because then we have a way to set apart different causal inference methods and see which one spit out the right graph. But then we still, up to that point when we will actually be able to implement the intervention, we will have a plethora of different models that might be compatible with the data. So, kind of, I don't know, if you think about the idea of, in the proper sense that you can falsify a model. If you ask a question about models that you cannot falsify, then maybe it's empty statements. But what does it mean concretely? You could just incorporate, let's say you have a TMS device. Instead of asking the question, can I do a separate study where this bolt activity or this cortical dipole activity causes a certain reaction time to be faster or slower? You could use your TMS device and do some studies where you have a TMS with a randomized position or signal. And then you could meaningfully at least talk about, should I intervene here or here to drive up the reaction time or to make a reaction time faster? But at that point, you still wouldn't be talking about the actual neuronal implementation of the faster reaction time. So it's kind of, maybe it's not that easy and meaningful to talk about, let's find the causality in the brain, unless we really know what we're actually asking. And often you need kind of a goal-directed question. If you have a goal, like where should I position my TMS device best to make this work, you have a clear question, and then you can decide between 4 compatible models. Maybe you can decide for the one that actually drives down reaction time with a certain TMS stimulation. And then you would say, this is clearly the better one, and the entailed causal relationships on the neuronal level by this one are the ones that I can trust the most. But until you can falsify, basically there's no way to tell apart these two stories. If you have 2 models that give you the right position for the TMS device, but different neuronal relationships, then you wouldn't be able to tell apart these 2 stories on a causal model world. So it gets very kind of problematic. So I think is why I prefer these kind of zoomed in, small, very concrete problems or questions that you're asking when you consider causality. If you want to know what's the effect of my cat photograph that I'm showing to subjects, then it's a concrete, precise question where I can actually do the intervention. I can check which causal model is the most powerful to explain this. If you just have this black box brain system, maybe it doesn't make sense to talk about causal models and preferring one over the other if there is several ones that are compatible with everything that you've seen so far. So that brings you down to equivalence class of models, basically. And the more interventions you can perform, the more models you can rule out as being compatible with your data. So I think the hope of all of this will be, if you find a model class that is compatible with your data, given certain assumptions, and all of them have one certain edge between this and this area, then you would be happy to conclude there's a causal relationship between this area and this area, because all models that I have claim that this is the case. But you wouldn't make any claim about brain areas where they have maybe conflicting statements about the causal direction. You would just say, as of now, I cannot tell apart this from this direction. It's kind of a safeguard. Yeah? Okay. Granger causality, something different now. Causal inference in time series. We'll briefly talk about Granger causality, but mostly about its limitations. Who knows about Granger causality? That's good. Gives me a good starting point. I'll start with probably the definition that most of you have seen. And hopefully most of you have only also seen the second one, but I'm going to start with this one. So what I call the simplified definition is one stochastic process evolving through time x is causal to a second one y if the autoregressive predictability of the second process at a given point in time is improved by including measurements from the past of the first. Sounds very cryptic. I'm going to try to explain it again with help of this formal statement here. So the prediction accuracy of yt given only the past of y is improved if you include the past of x. That's the definition of x being a Granger cause of y. So if you start with just a single autoregressive model and you include another variable and it gets better in prediction, you would say, okay, this variable is a Granger cause of my variable y. That is not the definition by Granger. It's not. It's really important. Here's an example why it's important. We have three time-evolving processes. Let's say we only observe the x process and the y process. We cannot observe the z process. Let's also assume the z process at any given point in time influences the x process at the next time step, but the y process, it influences 2 steps later. If we have this, then, okay, let's consider the prediction accuracy of yt given the past of y. So we're trying to predict yt plus 4, let's say, only from the past of y. And now we're wondering, does it help to include the past of x? Well, yes, because if we include this guy here, it'll tell us something about zt plus 1. It will explain away something of this edge, and it will help us improve the prediction of yt plus 4. So if that is our definition of when we say xt is a Granger cause of yt, then in this case we would say x indeed Granger causes y. The problem is, as you see, it doesn't. The way I put down the model, it doesn't actually influence. So why is that the case? Because we're not reading the actual definition, we're just reading a simplified version of it. The actual definition is a bit more tricky or abstract. Granger's definition is, we predict, let's just start here. I'll predict yt given the past of everything. And now I'm asking the question, what happens if I remove xt? Does it actually get worse? And then he says, if it does get worse, then of course xt must have been a cause of yt. So that's, the difference is here we are including another variable and asking, does it get better? The problem being, if there's unobserved variables, then it kind of mixes up our definition. And here, the problem is, of course, we don't have the past of everything. With this, we need to translate into an assumption, namely, we have observed everything that is relevant to the system at hand. If we have observed everything that is relevant to the system at hand, we can use this definition and say, okay, if we remove xt and the prediction gets worse, then indeed, there's only one way this can happen, namely when x causes y. There's still another problem. Yes?
So this is saying that the first definition, the working definition of Granger causality that people use, I think, quickly when they're trying to measure this, you're just saying it could be confounded. That's what you're saying.
Yes. So I'm saying it could be confounded. So either make explicit the assumption that it's not, or you're assuming it's not confounded, or it doesn't work. So that's the statement of that one. But there will be a more formal statement on the following slide. Yes?
So you could assume that in an experiment you measure another variable, and you have like an in-between version of the two statements where you say that, okay, if I remove x, but I still have z, and now I get a reduction in the predictability of y, then I can there may be some confound, but it's not through the other parameter that they're measuring.
Let me see whether I can clarify this. I think what you're saying is we can agree on what this world is that we need to observe to make sure that this cannot happen, this problem that I've just explained. If we agree X, Z, and Y is everything, that to make sure we don't run into this confounding problem, which means assuming unconfoundedness, then it still does work, yes. But we need to make sure or have plausible reasons to believe that we have observed everything.
Or my statement was more in the situation where we cannot observe everything. We don't know what other variables could be confounded between X and Y. We can say at least that it's not through Z.
Ah, yes. Okay, like partial statements. Yes. That does work still. Yes. Okay. So next time you read Granger causality, try to double check whether the paper mentions unconfoundedness or causal sufficiency, which is basically saying we have observed everything that we need. If not, then there is a discussion to be had whether it does actually make sense. There's another problem with Granger. Let's say we have only two variables. Let's make it even simpler. Let's say they depend on each other deterministically in the following fashion. So the X variable causes the Y variable one time step later, and the Y variable causes the X variable one time step later. So now what's the problem here? The problem is, if I set the X variable throughout time to a certain value, it will have an effect on Y. This value that I will set will influence this value that I set will influence this value. But with this Granger definition, X wouldn't be concluded to cause Y. Let's see why. So let's predict YT given the past of everything. So let's say YT plus 4, okay, the past of those two variables for the entirety of the past. Okay, we just need XT plus 3. Perfect, we can perfectly predict YT plus 4. If we now remove the past of X, okay, we're not given this guy here anymore. Let's just go one step further back. We still have YT plus 2. We can still perfectly predict YT plus 4. So the prediction accuracy does not decrease. Hence, X does not Granger cause Y. But if we intervene on this very system, there is an effect on Y. So the problem here is Granger fails to predict the effect of interventions. That is an example.
Yeah, but that's the thing. Neuroimaging wells, actually, how would that happen in the real world?
I don't think there is a real-world example that we can come up with. The aim is also not to say that Granger is like, just throw it in the bin and forget about it. The first step was to say, be careful about the assumptions. The second one is, at least from my standpoint, there's at least still a conceptual problem with this definition. We can argue about or rule out by assumption such contrived cases, but if you just write down this definition, there's still this conceptual problem.
Maybe one more comment on that. So if you change it to an almost deterministic setting, the qualitative argument breaks down, but it still shows that Granger causality does not correctly quantify the amount of causal influence, because you get a weak influence, although it's strong. Okay.
Any more questions? Okay, here's the more formal statement I was talking about. So assumptions, there's no common causes, no hidden common causes, and there's no instantaneous effects. And then you can check out the book and find this nice theorem that tells you if the distribution is Markov and faithful, so this is assumptions that we heard earlier on, all the conditional independencies are implied by the deck, and it's only the ones that are implied by the deck. If that is the case, then in this model up here, there is an arrow from the past of y to xt if and only if y Granger causes x, but according to this correct definition where you have observed everything that you need for this model, so there's no more hidden common causes. Then it does make sense. And I think we were just discussing, does that happen? We've set Markov and faithfulness assumptions, so we kind of ruled out these cases and then it does work. But we can, I think in this other world you can view and understand a bit more clearly what it means. Okay, more questions? Nope. Okay, then I think it's Dominik again.
Okay, and now you can forget for a moment everything we said before, because we forget about statistics. So far it seemed like causal inference is always about drawing causal conclusions from statistical observations. But if you look what happens in real life, Sebastian? Then it's not always about statistics. Thanks. So you see two objects and you observe they are pretty similar. So then you would infer there's some reason that they are similar. So there's common history that explains that. So we definitely agree that similarities require an explanation, so it's not always about statistical dependence. But the question is, what kind of similarity requires an explanation? So here you have similar patterns in a way, but nevertheless, nobody would assume that anyone has copied the design, because the design has something so straightforward that we assume everybody could come up with it independently. So we learned from that similarities require an explanation only if the pattern is sufficiently complex. But how do we measure that, whether a pattern is complex? Consider, for instance, a binary sequence and a hypothetical experiment where two persons are instructed to write down a string with 1,000 digits. And the result is surprisingly that both wrote down this binary word. So all 1,000 digits coincide. So the naive statistician would conclude there must be an agreement between the subjects because the correlation coefficient is 1 between the digits. This is certainly highly significant for sample size 1,000. So he would reject statistical independence and infer the existence of a causal relation. However, another mathematician recognizes that this was just the binary expansions of pi. And given this observation, in principle, both subjects may have come up with this number independently because it follows from a simple law. Whenever you see there's a law behind it, then it could be that both come up with this independently. Which means that superficially strong similarities are only necessarily significant if the pattern are not necessarily significant if the pattern is too simple. But how do we measure that? And one principled way to do that is Kolmogorov complexity. Kolmogorov complexity is basically the length of the shortest program with output x on a universal Turing machine, so an abstraction of a universal computer. And the interpretation is just, it's the number of bits required to describe the rule that generates x. And just to give an introduction to algorithmic information theory in a nutshell, in algorithmic information theory, you often see these kind of equations, which means that we neglect string-independent additive constants. So if you have a proof that some objects are equal, then usually it's not really equality, it's only equality up to a constant that does not depend on the complexity of those strings. So that's what we call O1 constants, O1 terms. Okay, so, and whenever two strings have low complexity, they cannot have much in common by definition, because they don't have much structure. And something that worry many people, k of x is uncomputable, so you can show there can't be an algorithm that computes the length of the shortest compression. Nevertheless, it's very helpful for many theoretical considerations, and we believe also for causality. And this is something that I'm going to explain. Kolmogorov introduced it as probability-free definition of information content. So after having developed all this, or a lot of these formalisms about probabilities, he decided there must also be a nice theory about information without probabilities. And also for causality, we believe that quantifying information without probabilities is something very crucial. We need also the notion of conditional Kolmogorov complexity. This is the k of y given x is the length of the shortest program that generates y from the input x. And you can easily see that k of y given x can never be significantly larger than y given than just k of y, because you could just include the information ignore x. So a program that just tells you to ignore the input x would provide the original program that just computes y from scratch. So, and k of y given x is just the number of bits required for describing y if x is given. And then there's another subtlety of algorithmic information theory, that you have to distinguish between k of y given x and k of y given x star. And x star is the shortest compression of x. And because there's no algorithmic way to generate the shortest compression of x from x, but only vice versa, it's always more valuable to have the shortest compression than having x itself. So what we need for algorithmic information theory, what makes it nicer, is to consider k of y given x star. It's the length of the shortest program that generates y from x star, from the shortest compression. Okay, so the subtle difference, because x can be generated from x star, but not vice versa, because there is no algorithmic way to find the shortest compression. And well, this is actually details, but algorithmic information theory gets nicer if you consider these expressions instead of that one. It's just more elegant theory. An important concept for our purpose is algorithmic mutual information. So the information of x on y or y on x is the compression of x, the length of the compression of x, plus the Kolmogorov complexity of y, minus the joint complexity. And fortunately, this is up to a constant the same as k of x minus k of x given x star, and this is the same as k of y minus k of y given x star. Don't ask me why. Yeah? Yeah? Yeah, okay. So just to finish that, for statistical mutual information derived from Shannon entropy, these equalities are just 1 or 2 lines proofs. But for algorithmic information theory, these equalities are very deep results. So don't ask me to explain that. Okay, and the interpretation of mutual information between X and Y is just, it's the number of bits saved when compressing X, Y jointly rather than compressing them independently. Okay, Fabian, your question?
My question was, you two slides back in statement strings that have low Kolmogorov complexity cannot have much in common.
Yeah.
Can you explain that?
In the sense they don't contain information, though, so they can't have information in common. In Shannon information theory, it would be the statement that the mutual information between 2 random variables x, y could be at most the Shannon entropy of them, of each of them. So it's just an upper bound. Okay, and just to visualize that, so if you have these 2 objects, what they have in common is the star. So the if you compress the, let's say, a program that generates those images, you need to code this one only once. So you can save this. And I already mentioned that there's a tight analogy to statistics. So if you replace the strings, which are just descriptions of objects in the world, with random variables and replace Kolmogorov complexity with Shannon entropy, then you can replace algorithmic mutual information with statistical mutual information and obtain basically the same equations, with the difference that everything rolls up to a constant and is just about individual objects. And now we stated the causal principle, meaning that if 2 strings x and y are algorithmically dependent, then they either have a common cause or one is the cause of the other, in this direction or in that one. So every algorithmic dependence is due to a causal relation. So it resembles Reichenbach's principle of the common cause on the level of individual objects. And the distinction between those 3 cases require conditional independences on more than 2 objects. This is also in analogy to causal inference with variables. Okay, but of course, I mean, you can just postulate that. I mean, we have discussed that for quite a long time and came to the conclusion that it's a reasonable postulate. But of course, whenever you postulate a relation between causality and observations, then it's the question where it comes from. Okay, and I think we can support that by the fact that there are more analogies to the statistical case. Okay, so what we also need is to make the analogy complete, conditional algorithmic mutual information. So the mutual information between x and y given z is k of x given z plus k of y given z minus k of xy given z. So that's the information that x and y have in common when z is already given. And you also have the formal analogy to statistical mutual information. And now we define conditional independence just as this algorithmic mutual information being close to 0. Then we postulated the algorithmic Markov condition. saying that if n objects, formalizing some observations in nature, are related by a causal DAG G, then every xj is conditionally algorithmically independent of its non-descendants given its parents, so xj independent of ndj given x star. And then we were able to show the following equivalence of algorithmic Markov conditions. So for n strings, the following conditions are equivalent. Local Markov condition, so this conditional independence. The global Markov condition, so that d-separation implies conditional independences, but here for sets of objects rather than individual objects. And then we have the recursion formula for the joint complexity, meaning that the joint complexity of the n objects is given by the sum of the conditional complexity of every object given its parents. And this replaces the factorization of probabilities into conditional probabilities given its parents. Okay, so from that point of view, the analogy to the statistical world is complete. However, there's still one block missing, and this is the following. So, if you remember, when I was introducing the probabilistic graphical models and the 4 different Markov conditions, we had 4 different Markov conditions, and the first one was the existence of a functional causal model. And if you recall that, the functional causal model was a model where every node was a function of its parents plus an unobserved noise term. And the existence of this model implied that all the 3 other Markov conditions hold. Okay, and this is in a way a justification of the Markov condition. So, it's a matter of taste which postulate you consider more basic. But in the statistical world, I think at least Pearl considered it more basic, that he started with this deterministic model and said, if I demand that the noise terms are statistically independent, then the other 3 Markov conditions follow. And from the conceptual point of view, I think it's a fair point. If you work with it, you see that these deterministic models are easier to interpret than the probabilistic models. So it makes sense to start with this as the most basic principle. But, okay, so for that reason, because we thought it's a good justification, we tried to copy that into the algorithmic world. And indeed, it was not really difficult. And we came up with the algorithmic model of causality, meaning that if you have n strings related by a DAG, then we postulate that each string can be computed from its parents plus an unobserved noise object. So maybe one shouldn't call it noise, it's just an unobserved object that determines the mechanism. One could also say, so T stands for Turing machine. So the Turing machine gets the input, the values of the parents, so the parent objects, and an unobserved object. So you can read it also this way, that the unobserved object is the mechanism that describes how xj is generated from its parents. And then we postulate that all this uj, this unobserved mechanism descriptions, are algorithmically independent. And keep in mind that this is the analog of the noise term in the statistical functional model. And then one can show that if n strings are generated by such an algorithmic model of causality according to the DAG G, then they satisfy the 3 equivalent algorithmic Markov conditions. So in this sense, we have completely resampled the graphical world, the graphical model world, and considered this as kind of foundational formalism for causality. Any questions on that so far? Yeah?
This might be a slightly more general question, but I think something that you said probably just phrased it out in me. You drew a nice analogy between Shannon information and Kolmogorov algorithmic information theory. So I'm trying to think, one of the main questions, let's say, still in Shannon information theory is the definition of those quantities for the multivariate case. So if I had 3 variables, what's the new?
Yeah.
How does that translate in the Kolmogorov case? And are there some of the assumptions that actually get rid of this problem?
So the short answer is there is no problem, but that's not what you want to hear, of course. Or put it this way, I'm not sure which problem you mean. I mean, for variables, you just have, of course, the joint entropy is not the sum of the individual entropy, and this difference is exactly what mutual information measures. Or if you have multiple objects, it would be I think it's called multi-information, right? I'm not sure about that, yeah. So, and this would perfectly translate into the algorithmic case. So maybe I don't get the problem.
Yeah, I think, when you were defining mutual information, I think a few slides ago,
yeah.
and trying to translate that in terms of more complexity. So in the examples, you're always using 2 variables, x and y, x and z, y and z.
Okay. Yeah.
What happens if I had 3 of them and they simply do not nicely factorize, so that I can take pairs, like one pair?
Okay, but I don't think that there's a substantial difference. If you have, let's say, pairs of random variables. Let's say you measure the information of x, y, and let's say the w. It's just entropy of xy plus zy minus entropy of all together. And
I'm just thinking about the case x, y, z. So mutual information of x, y, z, let's say. But yeah, in that case, you're assuming that x, y, that there is no synergy between x, y, and z.
I would look at it this way. From an abstract perspective, it doesn't really matter whether you consider pairs of variables or variables. We haven't specified the range anyway. So, if x alone is already vector valued, then you have the same thing anyway. So, I'm not entirely sure what you mean by synergy. So you can, let's say, this information could be split up into information of x z plus information of y z given x.
Yeah, we can probably talk about that later, but
yeah.
yeah.
Yeah, but Yeah, but the short answer is that all these equations translate perfectly. There's no issue at all. Yeah. Yeah. Okay. Yeah. Yeah.
So if we tie back to the previous example about binary pi.
Yeah. Yeah.
So the question is to equal they're not causal because we have this simple encoding.
Yeah. Yeah.
Through this.
Yeah.
Can you spell it?
Okay. So, okay, maybe. Of course, that depends on your Turing machine, but usually I would assume that for a reasonable Turing machine, pi has low Kolmogorov complexity because there is a simple room. Yeah, it's a constant anyway, but of course, in practice, it doesn't make sense to talk about constant versus non-constant. This is a bit difficulty in translating between math and what you do in practice. I mean, what in the mathematical world is just equality up to constant should be interpreted to as equality up to a small term. But then, yeah, it's the same as in statistics. It's always the question. I mean, for statistical dependence is something that refers to an individual, to an infinite sample, and for a finite one, you have to set the threshold. So I think there are also issues that perfectly translate. But I'm not sure whether this answers your question.
So if we have subject A and B also writing this down, then their lengths would be all pretty low. So if you're encoding
Yeah.
A and B, the paired encoding would also be very low.
Yeah, that's the idea. So, okay, if those two strings were random numbers and they still coincide, then they share a lot of mutual information, which defines a strong evidence for a causal relation. So this is what I meant. Yeah. More questions on that? Okay. Okay, we have this analogy, and this is basically just a visualization to show that it's not always statistics. So let's say you have 3 carpets, and you just observe which parts of the pattern occur in all 3 of them, or which ones that occur in A are also in C, or maybe, and then you can talk about conditional independences in the sense that the only thing that A and B have in common is the star, but this star occurs already in C. So in this sense, A and B are conditionally independent given C. And I mean, regardless of whether you like Kolmogorov complexity, I mean, there's of course these concerns that it's not computable, and I will also talk about why it's nevertheless relevant. But forget about Kolmogorov complexity for a moment. What this example nicely shows is that there are quite general notions of conditional independence. And you can talk or you can ask, whenever you define a notion of conditional independence, should we postulate a Markov condition with respect, a causal Markov condition with respect to that notion of conditional independence. Just to show the generality of this concept of conditional independence, you can say I measure the information of two sets S and T. So let's say these are just two sets of objects. I measure as number of elements in common. Number of elements, or let's say just the number of elements they have in common. And then I can define a conditional information between ST given U as the number of elements they have in common apart from those that are in U. And we had a paper some years ago that generalizes this algorithmic stuff in the sense that we considered general information functions and how they define notions of conditional independences. And basically the result was whenever you have a submodular function, I don't want to go into submodularity now, but just to mention, under some mathematical properties that are quite well studied in optimization, you can nicely define a general information measure and in principle postulate a Markov condition with respect to that measure. But then the big question is, why should this Markov condition hold with respect to the real world? And we showed basically that whenever you consider a class of causal mechanisms that fits to that particular information measure, it makes sense to postulate a Markov condition with respect to that measure. I'm not going to the details here, but yeah?
A question for when you're done with
Yeah.
So I guess what's puzzling me most about this information theoretic, or algorithmic information theoretic approach in general, is that it seems like you're saying I can say something about the independence of individual objects.
Yeah.
Before it was only independence of distributions of things. So I had to look at larger and larger sample sets to be able to determine if two random variables are independent. But here you're able to say that one object is dependent on one other object.
Yeah.
I'm having trouble reconciling that. And I guess the example would be, what if I have a distribution of carpets and I'm sampling a bunch of carpets, and carpets A and carpets B? Is that the same problem?
No, it can be related. Okay, so it's not the same problem because this algorithmic dependence adds an additional level. So if you sample carpets, you can have similarities on the level of individual carpets, and you can have a statistical dependence, but these are two different things. There is a relation between Shannon entropy and Kolmogorov complexity in the following sense. So let's say if you sample 0 and 1 with some probability measure and you have an independent sampling, then you can show that the Kolmogorov complexity of this binary word divided by the length converges to the Shannon entropy of, let's say this is the random variable x. So asymptotically, the entropy generation coincides with the Kolmogorov rate. But this requires some individual sampling or some weaker form, some ergodicity of the source. But for the general object, you don't have that, which you can see from the following example. So let's say you have 10,000 symbols 0 and 10,000 symbols 1. So if you think of it in terms of Shannon entropy, then half of the bits are 1 and half of them are 0. So Shannon entropy would be 20,000, but still it's highly compressible. So there's not much structure behind it. Okay, but I've been promising that although Kolmogorov complexity is uncomputable, there's something that is useful in practice indirectly. And I still owe you to show that. Okay, if you recall previous slides on the independence of mechanisms, then we had the statement that P of cause and P of effect given cause are independent in the sense that they don't share information. And I briefly mentioned that we formalized that by algorithmic information. So this is definitely not the statistical information, because we are not talking about the statistical dependence between C and E that we have anyway. Otherwise the problem would be trivial, but we are talking about those two individual objects. And we showed for several toy examples that it makes sense to talk about the Kolmogorov or the algorithmic mutual information between those objects. And we postulated that usually if this is the right causal structure, the right causal hypothesis, then you should have an algorithmic independence. For the additive noise model, I mentioned that if you choose P of C and P of E given C independently, then it's unlikely to have an additive noise model in the backwards direction. And we formalized this idea by showing that we have algorithmic mutual information between those objects if they satisfy an additive noise model in backwards direction. So in a way, you have a foundational principle that can be used to show that the causal inference methods make sense. More questions on that? Yeah? I think you have to repeat it or bring the microphone.
Just like when you try to calculate the shortest length to compress your object, does it require some assumption about the possible space that your object can live in? Like, how do you get this length in general? Like,
question. So first of all, I'm not sure whether you referred to that. You need to specify the alphabet you use for the description. I mean, for Kolmogorov complexity, it's usually just binary words, so you have just 0, 1. But in general, you need a rule how to translate it from a higher alphabet, a more complex alphabet. Yeah, of course, I mean, all these questions are related to the question which Turing machine makes sense for your application. And yeah, you have to just interpret it in a sensible way. This is maybe all I have I can say this regard. Yeah. Okay. More questions on that? And maybe something now about that is a bit closer to applications than these ideas. We already considered some empirical compression algorithms and did toy experiments where we had, for instance, several versions of an abstract and computed Lempel-Ziff compressions and defined mutual information using this compression length, and the outcome kind of made sense. So, but this is more proof of concept so far. Yeah, I think we went through the slides a little bit faster than expected, maybe because there's a lot of stuff that I already presented several times. I tend to get faster every time, so you need to stop me then. So take-home messages. Graphical causal models do not solve the hard causal problems, but they provide a clear framework to address them. And subject to strong assumptions, causal structure can also be inferred from passive observations. However, machine learning, one is used to rely on strong assumptions anyway, so one should not shy away from strong assumptions. So, more questions on that? Yeah?
Well, is this an okay time to ask kind of review questions about?
Yeah.
So I was wondering if we could revisit this concept of faithfulness.
Yeah.
I understood it the first time.
Okay, so this is about this incidental cancellation of dependence, because the fine-tuning of the parameters. So you have, let's say you have an independence here, it's x independent y, that is not entailed by the structure, but just due to an unlikely cancellation of different paths.
Okay,
And this is
Z is somehow perturbing, or somehow linked to X in such a way that it's, it's canceling out any statistical dependence. You might
Yeah, I mean, you can specify it very explicitly. So let's say you have a linear model, and here you have alpha, here you have beta, and here you have gamma. Then alpha needs to be the same as minus beta times gamma, and then it cancels. Yeah.
But so later on, though, I thought you had an example where you had maybe an assumption that X and Y did not have a link. I think it arose in the context of the acyclic ICA. You had assumed, if you can do that for it, can you forward this slide?
The ICA slide?
Yeah, there. Sorry. S is not independent of X. It implies that there is
no. The brain, the neuro thing.
Before that,
that
there
one.
it is.
Yeah.
So assume we find that S is independent of X. It implies the existence of a path between S and X. So is that an example of faithfulness as well? I thought I produced it that's related to the assumption of faithfulness.
Yeah, you need faithfulness, right?
We need faithfulness. So for this to work, we need faithfulness. I don't know, let me rephrase first faithfulness maybe in a more like colloquial slogan. Nature doesn't hide away causal relationships.
Nature doesn't what?
Hide away causal relationships, which it would if these guys would turn out independent, but there is actually causal relationships. And here we need faithfulness to conclude from the conditional independence that we observe that indeed all paths now between S and Y need to be blocked by X. If we don't assume faithfulness, there could still be other paths, but for some magic fine-tuning reason, they cancel in such a way that once I condition on X, S and Y appear to be independent, but they're not actually functionally independent.
Is that the last item there?
That's the one.
But what about this first item here, this first implication? Does that have something to do with faithfulness?
No.
Because that's what it's about.
So the first two ones are actually kind of, okay, so the extreme case will be you can model any conditional independent structure by the fully connected graph if you don't insist on the conditional independencies actually being represented in the graph.
Okay.
So for this, you don't need faithfulness to conclude from dependence that there is a path, but vice versa, you need. Yeah. So kind of you could say this direction is Markov condition. So these are working basically in both directions to make a bi-implication between graph properties and conditional independence statements.
Okay. Yeah.
Maybe just another clarification, like to follow up on this. Is it, so this condition of faithfulness, I mean, as far as I'm getting it, is quite well formalized in terms of facts. When it comes to, so considering the connection that you made between causal implications and ICA, do you have like the same sort of like well-defined definition of faithfulness in ICA, as in, well, I need to have these many assumptions, otherwise ICA is going to be a terrible model, and whatever I extrapolate with my terrible model is going to be completely rubbish when it comes to causal implications as well. I don't know if it makes sense. Let's say I'm trying to use ICA when all of my variables are Gaussian. It's not going to be great. So let's say in that case, the causal model you extrapolate is also not going to be great, I assume. So does the ICA also need to be faithful to, you know, the actual problem you're trying to solve? And is it well defined? Like, is this, you know, set of conditions for ICA just the same as faithfulness? I don't know, maybe I'm just going around this.
Okay, I'm not sure I fully understood your question, but let's try. So faithfulness is an assumption that links properties in the graph, these d-separation statements, to conditional independencies that you expect to observe in the distributions. So then these conditional independence-based causal inference algorithms try to exploit this to go from observations or statistics of observations to the causal graph. Then ICA was different, so we change gears. We start with a different set of assumptions and also try now to go from observations to a causal model. So here you kind of don't clearly see what it means to be faithful, because you're not talking about the graph and the joint distribution and about these conditional independencies being entailed the only ones by the graph. I'm not sure what in this context is the right way to think about faithfulness. Do you still have, once you run your ICA, you get one graph basically?
Yeah.
That has some d-separation statements?
Yeah, maybe one comment comes to my mind. When I presented additive noise models many years ago, then one of the people who invented faithfulness, like Peter Spertus, said, "Oh, it's basically like faithfulness." And but what he meant is not in a literal sense that it's really based on faithfulness. It was more that it's in the spirit. And I think how I would phrase it is that faithfulness and the independence of mechanism, that this is closely linked. So faithfulness is also a kind of independence of mechanism. So you could think, for instance, of a model that is entirely nonlinear, but looks like a linear model from the wrong direction. So it's the same as the nonlinear additive noise model. And to exclude that is, of course, in the same spirit as faithfulness, because it's just accidental, and you reject that, but not really based on it. Yeah. Yeah?
Can I ask a very just philosophical question?
I like philosophical questions.
So one of the things I appreciated from reading some of the stuff that Phil wrote was how late causality appeared in physics, if at all. Like he had some examples of just sort of the absence of causal relations in many of the most important theories in physics. And I brought up the example of systems of differential equations. A kind of case where the causality it's unclear how it's related or what its utility is in analyzing such systems. So that brings, to me, that brought up the question is again, this is why it's philosophical, is causality actually something in the world, or is it something that our brains, sort of glue or impute? So because it helps us to do things. It helps us to make decisions.
Yeah. I was laughing a bit because, in the early days of our causality research, we had a lot of questions like whether causality exists at all. Yeah. So usually it was the case when people were coming to the department and having highly technical questions with all the other groups. Then in the evening, they just enjoyed to talk to me about whether causality exists at all. And no, yeah, sure. No, I appreciate that. I think physics has a bit of historical burden because there were famous physicists, like for instance Russell, or philosopher and physicist, who tried to abandon causality from science. He considered it, I don't think, something else, something metaphysical. But I think he revised his opinion to some extent later. But this you don't hear that often. And what I learned during the past decade, for instance, when I was talking to a lot of physicists in quantum information theory and so on, they are reintroducing causality into physics again. And it's much more considered physics nowadays. And I was also trying to fight for that. For me, causality and thermodynamics is tightly linked. And Reichenbach, I think, recognized a lot of these links. And we elaborated on that. And I still would like to consider theory of causality also as part of theoretical physics. Yeah?
A very practical question for analyzing data, for example, can we have a procedure that can avoid very many confounding factors based on theories?
Thanks for the question, Matt, because this is one comment I forgot to make. So what sometimes helps to address the problem of confounding is to make strong model assumptions with strong conclusions that would usually fail if there is confounding. Just to give you an example, if you have the hypothesis that X, let's say, X influences Y. You observe a dependence, but of course you don't know whether there's a common cause. And this is, of course, one of the hardest problems at all. And then what would help, let's say, if you discover a variable of which you believe that it lies in between, that so you just look at the mechanism, and then say set, and then you observe that X independent Y given Z, then you haven't shown that there is no confounding, but it makes confounding much more unlikely, because typically that would screw up the conditional independence. And this is something that I think also on the philosophical side, when you read Karl Popper, then the idea was in Popper is often that scientific hypothesis is never confirmed but only falsified. And whenever a hypothesis allows many options for falsification and all the falsifications fail, then it's a strong hint in favor. And I think this is a bit in the spirit. So whenever you have models that have a lot of implications, so a lot of options to falsify it, and the falsification fails, then it's a strong hint. And that's maybe one of the strongest things we can do in causality. That's at least my current take. You're welcome.
Well, that brings us to the end. So let's thank our...
Thanks for your attention.